So welcome everyone to the IAHR online course on modeling software for transient flows. We are very happy to have you here to see so much interest in this important and complex topic. First of all, I would like to thank all the speakers for their availability and valuable contribution to this course. This is the third course organized by the IAHR Working Group on Transient Flows and the first to be launched under the new IAHR Training Courses series. In a few moments, Mohamed Ghidawi will give us a preview of the upcoming courses in this exciting new initiative. Let me briefly introduce the IAHR Working Group on Transient Flows. Our mission is to foster research, training, and collaboration on hydraulic transients, focusing on innovative diagnostic methods for real-world systems. As you can see on the slide, we cover a wide range of topics from wave theory to fluid structure interaction, computational modeling, transient turbulent flows, and field-based applications. This course is one of the key expressions of our activity. We are also finalizing a monograph on transient flows developed with the contribution from nearly all the lecturers of our first course. In addition, we regularly organize special sessions and thematic meetings to keep the community connected and growing. I'd like to highlight our upcoming meetings. First, we'll be present at the next IAHR World Congress in Singapore in June. This is a great opportunity for the transient flow community to share research and connect with the broader hydroenvironment network. Then, from November 25th to 26th, 2025, we will host the International IAHR meeting on transient flows in the Greater Victoria Metropolitan Region in Brazil, in conjunction with the 26th Brazilian Symposium on Water Resources. Victoria is a lively city in the southeastern Brazil, known for its beauty, nature, and relaxed lifestyle. You are warmly invited to submit your extended abstract. You have time until June 9. You can scan the QR code to access more details. The main themes include artificial intelligence, case studies, experimental methods, innovation in transient control, leak detection, modeling software, and pipeline design and protection. We look forward to welcoming you for these 2 days of rich technical exchange and meaningful connections. Finally, I'm pleased to announce our flagship conference, the 15th International Conference on Pressure Surges, to be held in April 2026 at the Deltares campus in Delft in the Netherlands. This is a key international event for the transient flow community, and don't miss the opportunity to be part of it. And now I'll pass the floor, or better the screen, to David Ferras.
Thank you very much, Silvia. With this slide, I would like to provide a bit the numbers concerning the registrations that we got for this course. These are numbers, by the way, from Friday, where we had 300 registrations. Now, from this morning, we had around 370. So in the left, you can see the geographical distribution of the participants. And it's nice to see that besides Asia Pacific and Europe, we have also a good representation from America and especially from Africa. In the top right, you can see the breakdown concerning industry versus academia. There are around 45% of participants coming from industry. This is an indication of the high interest that the topic on transient flows modeling software, so the topic that comes from the practitioners. And then also we have the figure concerning IHR members versus new IHR members, because at the moment of registration, there were more than 100 participants registrations that were not originally IHR members. So I would like to give a warm welcome to these new IHR members. And I would like also to invite them to participate in the many activities that IHR organizes throughout the year, like the World Congress, as Silvia mentioned. It will be held in Singapore by the end of June. Also, the HR Young Professionals Congress, which will be held online. It's held every year around by the end of November. And then also the regional congresses in Europe, Asia, Africa, Latin America, and the many technical conferences organized by the technical committees. Also, IHR manages 7 scientific journals and a magazine for scientific dissemination, which is the Hydrolink. By the way, a couple of years ago, there was a special issue on transient flows, and as IHR members, you have access to it. Sylvia, you can pass the, thank you. Now we have ahead this program that in few minutes, Mohamed will provide his talk on introduction to water-hammer theory and modeling. Then Anton Slice, Brian Carney, and Brian Saint will provide their talk on more oriented to applied research, providing examples. Hanif Chowdhury will explain a software which is the result of a long-standing development, very much based on his book, Applied Hydraulic Transients. And for Tuesday, we have 3 speakers. The first one, Yuwon Chen from Wuhan University, who will explain CFD application for transient flows. Then Sam van der Zwaan, who will introduce Wanda, which is a software developed by Deltares. Christophe Nicolet, who will introduce Simpson, which is a software developed by Power Vision. For Wednesday, we have a similar setup, 3 speakers. The first speaker, Can Can from Hohei University, also providing an application from using CFD software for pump storage scheme. Enrique Cabrera, who will explain Algavi software, which is a software developed by the University Polytechnic of Valencia. And Trey Walters, who will explain AFT Impulse software. For Thursday, we have 2 sessions. The first one concerning Autodesk software by Professor Shang Huang and Nathan Gertz. And then Lina Sella, Lu Xing, and Gerardo Riano will talk about TSNet software, which is a library for Python. Finally, on Friday, there is a talk from Slavcho Velikov, who will explain Hammer, which is a software for water hammer modeling developed by Bentley Systems. And finally, we will have a roundtable being formed by Hanif Chowdhury, Brian Carney, Bruno Brunoni, and Jose Adriasola. And also all the speakers will be invited and welcome to join this roundtable, which hopefully will follow a richful discussion based on the diversity of our speakers and the high quality of our invited guest lecturers. Finally, I would like to give thanks to the sponsors of this course, Deltares, Bentley, and Power Vision, and also the China Society for Hydropower Engineering and the Centro de Studi de Sistemi Idrici, which are national associations also supporting this initiative. Said this, I hope you enjoy this very intense week. And I would like to pass the word now to Professor Brunoni, who will be chairing the first session. Thank you very much.
Thank you very much, David. Good morning, good afternoon to everybody. It's a great honor for me to start with this very important initiative, IHR initiative. And let me introduce the first speaker, Professor Mohamed Ghidawi. He's a Chinese estate professor of engineering and chair professor in the Department of Civil and Environmental Engineering at the Hong Kong University of Science and Technology. He had his PhD at the University of Toronto, Canada, and his general interests are in the field of water resources and environmental fluid mechanics. And he was the editor of the flagship journal of the IHR, Journal of Hydraulic Research. And he was awarded of the Arthur Rippon Award and several other. His contribution to the field are very important, and many of his papers are seminal papers. So please, Professor Ghidawi.
Thank you, Bruno. Thank you, Sylvia. Thanks, David. Good afternoon, good day, good morning to regardless where you are. It's nice to see you all. Let me maybe if you don't mind, we'll just share this. We also I second what David said. We would like to welcome all the new members and every one of you to this course. As you're aware, IAHR has been around for 90 years or so, and it has done great in publication, symposiums, congresses, and so on. This year, we've been working quite hard to introduce a new initiative related to education. So we would like to introduce regular training courses to our community, the engineers, the academics, the young professional, and so on. So you'll see a variety of courses. We're so lucky, as we were thinking about this course, that Sylvia and David were already planning this course. So we actually joined forces towards the end. And I think it's not new to you, the colleagues here, those listening. The tradition of transients, it started with hydropower, and then it went on to pipeline hydraulics. And I think it's doing a full circle now. It's going back to hydropower, and there is therefore a strong interest and support from the Chinese Hydraulic Engineering Society. I was in one of their conferences recently, and after a long search, they went back to basically pumped storage is the best battery you can have. So transient and for hydropower is back in fashion as well. Now, there are a few upcoming courses. The first one that's already organized, it will be actually in August 10th to 23rd, 2025. It's quite an interesting course. It has 6 days of classes and 5 days in the field. This is going to be at Three Gorges University, which is next to the Three Gorges Dam. And therefore, we have access to Three Gorges Dam, Gazebo Dam, and a lot of the hydro projects. This is near Wuhan, and this is where a lot of the big hydropower projects in China will be. So this course will be actually a mix, and it will be watch on demand. We're also in the last quarter of this year, we're already planning on a course on environmental fluid mechanics and another one on river confluence and shallow mixing interfaces. So this what we'll do for this year, and we'll start planning already for next year. Now, sorry. What? Sorry, we're having a problem here with the screen being stuck. So it's all right. As this is a course on transient. Okay. As this course in transit through model, so let's very quickly get you up to speed about at least my perspective what a model is and what it can be defined as a thing and can be an idea, process. Often for us, it's a set of equation or a physical model to try to imitate or mimic reality. Our reality is a pipeline, for example, or hydropower that we'd like to approximate. Why do we model? We like to understand and anticipate the effect of our actions. For example, what will happen if we close a valve? What will happen when we start a pump or a turbine? What will happen when these suddenly close? We like to control, and that's something we do all the time, control pressure, control flows, and so on. We like to predict events, transient scenarios. So all of these are some of the things that come in under transient flow modeling. Professor Gray and Gray nicely summarized this, basically define a model as a simplified representation of a region, a process, or a system of interest for the purpose of gaining understanding, insight, and predictive ability. Now, when you go to modeling, there is always the tension between simplicity and complexity. And like with anything, too simple, overly simple, yeah, you're gonna have very little parameters, very nice to do very quickly by hand and so on. You probably don't need computers, you don't need advanced physics, but of course your accuracy will be not great. We can go to the other limit as we go to the very complex models, multidimensional model, include nonlinearity, you end up with lots of parameters, very difficult equations to model. Sometimes you don't even have the parameters you need to model them. So although you have more physics, but you end up getting more errors because of the complexity, because of the need of parameters, because you don't know the geometry very well. So there is always a sweet spot in the middle, and that's what you will be looking for. That's what modelers really look for. And this is nicely summarized by the old statement of Albert Einstein. We said everything should be made as simple as possible, but not simpler. So again, we are always thinking, make it as simple as possible, but nothing simpler. Now, to get into transient, let me just start with a simple example, because what really got me interested in this is, as you will see, there is even a mix-up about whether we do even exist as a group. We know we exist, but others don't believe we exist. They don't believe that there is compressibility in the water, right? As I will show you even in some books. So this is now how I go around and try to convince people who are still not convinced that compressibility is at play. Let's consider a pipeline, which is 1 kilometer long, velocity 1 meter per second, area is 1. I'm doing this to make calculations very, very simple. So we get essentially the momentum is 1 million Newton second. How large is this momentum? Well, it's easier to see it if we compare it with the momentum of a car. An average car that moves at 100 kilometers per hour, it actually has a momentum of 28,000. So it's actually much smaller than the momentum, of course, that is carried by that one pipe. If you divide this momentum by the momentum of the pipe, you find that essentially the momentum in this 1 kilometer pipe is equivalent to 36 cars. Okay, stuck together. So in Hong Kong, we have 8,000 kilometers of pipes. So you could imagine, you could multiply it as to how many cars are already moving around constantly in our cities. Now, what transient happens is when we are trying to stop these cars, when we are trying to stop this water, we generate large forces. You know, if you suddenly stop these cars, you generate large forces. So it is with the fluids. Let's therefore, so let's say we're gonna actually, again, we stick with this example for a bit. Let's say we're gonna linearly decelerate this water. We're gonna stop it over a time delta t. Okay, so that Newton tells us that the force is the rate of change of momentum, the initial momentum minus the final 0, because we're gonna stop it, divide by delta t. So now here, we already said it's 1 kilometer, 1, and so on. So we get basically this 1 million divided by delta t. So if you do nothing, if your time essentially of stoppage is infinity, there are no forces being generated, the obvious. If it takes you an hour to do this, you generate a force at 280 Newton or a head of 0.028, negligible. Now, as you get time shorter to 60 seconds is still reasonable. When you get to 1 second, you get something you probably are familiar with, of the order of what we know from Warhammer waves, 100 meters. What's interesting, of course, this equation does not stop us from keeping to reduce delta t. So if we make delta t 0.001, we get a force of, 1 billion or 100 kilometers of head. Well, I think all of us who are sitting here and listening will agree that that's nonsense. Something is going wrong. And when you see these numbers going crazy, often what you should look is at least one of the assumptions that you made went berserk. What's the assumption here? I'm going to claim that is the density. We're assuming that rho to be constant. We need to relax that. The flow cannot, these forces cannot go to infinity. So one of the assumptions got to give, and that assumption, I'm going to assume that it must have to do with compressibility. Despite now, remember, we're dealing with Mach number much less than 1. So although Mach number is much less than 1, I'm going to assume that the flow, and this is going to upset a lot of people apparently that still don't believe in this, So I'm going to assume that it's still going to be compressible. If it is compressible, it means you must generate waves. If you generate waves, then your time scale is limited by the length divided by the wave speed. So you are not really allowed to get your wave speed or the time to go to zero, essentially. So your force becomes rho ALV divided by delta T. That is your time scale. And surprise, surprise, you discover your pressure, rho VC, or the famous equation to ask the Joukowsky. So in fact, the idea, what happens is that compressibility or Joukowsky actually limits the forces. In fact, compressibility is a blessing for us because what it's trying to do, let's say water was rigid, then you need to, if water were to be rigid, infinitely rigid, when you stop the column, you have to stop that 1 kilometer column all at once. That is a huge force to stop at the same time. What compressibility does, it stops it in sequence. It stops a bit of a time as the wave travels through, and it puts a limit. So no wonder structures, material have elasticity and so on. They all there to help us. Now, I assume that, let's see, actually, this is why because you all read books. So let's go through, for example, this book by, you see the author is here. It says if Mach number is less than 0.05 or so, compressibility effects are not important. That means we don't exist because our Mach number is much less than 1. This book in Fluid Mechanics by White, it says, we found that proper criteria for near incompressible fluid is when Mach number is much smaller than 1. So again, it implies that when Mach number is very small, that compressibility effects are not. But I just shown you that we need compressibility. This is one actually that rejected my proposal last year, and this is the argument. Says Mach number is between 0 and 0.005 is basically an incompressible flow. So he thinks what we are using is a wrong model altogether. So believe me, these are still in books. There are people going around. It may surprise some of you. It may not surprise others. Now, here is one where it's reasonable. It says incompressible flow, Mach number is much less than 1. This is correct. Because we will see that if it is incompressible, indeed, Mach number will be. But if Mach number is much smaller than 1, it does not mean it's incompressible. Of course, you always, when you get these things, go to the greats. This is a book by Landau and Lifshitz. And Landau, he says, if Mach number is less than 1, the flow may be regarded as incompressible. But he makes it clear that this is for a steady flow. Then he says, or they say, in a non-steady flow, further condition must be fulfilled. The time scale L over C taken by the sound wave to traverse the distance L must be small compared to the delta T, what I call delta T, he calls a tau, okay? So that means he can only treat as incompressible when we close these valves slowly, right? And that's in our language. The other person who has done really some great work on this is the book by Batchelor. I looked at many books. There is nobody who's done it as elegant as the book by Batchelor. And you should look on his page 167 to 169. Essentially, he starts with the general mass conservation, momentum conservation. He says, he puts the condition for compressibility, incompressibility. If it is incompressible, it means this is 0 and this is 0, right? So he scales, therefore, the gradient of velocity must be then less than a velocity scale divided by length. That means also the derivative density must be also much smaller than the velocity scale divided by length. Then we do what we always do in Waterhammer. We take the chain rule, we differentiate density with pressure, and that gives you 1 over wave speed squared. So we can move forward. Now we get the dp dt. You can use the chain rule of differentiation, and you get the partial derivative, which we are all familiar with. Or if you are not, you will see it in many of the other lectures in this course, plus v gradient of p. Now, this is the clever thing that he does, Bachelor, is because so far we only used mass conservation. So now he introduces momentum. Okay, he uses gradient of P, but gradient of P is given by momentum, so he replaces it here. So now you have, therefore, the full equation are come into play to do this, and you end up with 3 terms. So he says if these 3 terms are going to be less than a velocity scale over length, each one of them must be less than that. So we have 3 conditions. One of them is indeed the Mach number that everybody is happy with. The other one is the time scale. So if you want the flow to be incompressible, you must have Mach number to be much smaller than 1. You must have the time scale of your perturbation, your valve closure or whatever, to be much larger than the maximum of the L over C or Mach number L over C. But if Mach number is already less than 1, then the one that governs is L over C. And the third condition is that the GL over C squared must also be less than 1. This is not relevant to us, but it's relevant in where you have very deep flow, like in the atmosphere, where you have the length, and it could be 10 kilometers, 12 kilometers times the gravity, divide the speed of sound, then compressibility. So that comes in when you have lots of fluid piled up. So therefore, the fluid is incompressible when these 3 conditions are satisfied. It is compressible if any one of these is not met. This is where we belong in transient flows. We belong to delta T of the order level L over C, despite Mach number being smaller than 1. This is much smaller than 1. We still need compressibility. People in gas dynamics, they break mostly the condition of Mach number larger than 1. And people in dynamical metrology, they consider compressibility because of this fact. People in acoustic, by the way, all of acoustics are like us. When I'm speaking here there are students listening to me, of course, the velocity I'm generating is very little, right? In terms of velocity of air. So surely the Mach number is very, very small compared to 1, yet they still all hear me. So now, therefore, we can look now at all of the regimes, delta T. So this is the time scale. When delta T goes to infinity, we have a steady flow. When your delta T of the order of L over V, right? Or between, so this is between the advective time scale and the turbulence time scale, we get quasi-steady flow. If we go below this, between this and L over C, we get the rigid water hammer column. When we go below the length scale of the pipe, we get the water hammer. And if we go even further and we make our speed, our time to be of the order of the diameter of the pipe divided by the speed, then we get 2 and 3 dimensional waves. You actually get waves, and this will be for 10 kilohertz, 20 kilohertz, something we've been working on for the last 5 or 6 years. Now, the other thing that you find messed up a lot in the literature is most people, when they do pressure scaling, they will always jump in Bernoulli scaling. They say pressure is rho v squared. I warn you against that. I've seen published papers on transient that do this, and that is wrong. The correct scaling is actually rho v L over delta T. Rho v L over delta T. So when your delta T is of the order of L over C, your pressure scales correctly as P is rho CV, or you divide by rho G and you get the Joukowsky. So you get the Joukowsky scaling. When you are operating on a very small time scale of the advective time scale, then you're getting a Bernoulli type of scaling. Now, the other thing I like to have hopefully introduce or talk to you about is the water hammer model in the last 30 or 40 years have been used more and more for inverse analysis, for parameter estimation, defect detection, and so on. Yet, whenever you talk to a mathematician, all models are ill-posed. And there is a lot of trouble that comes to that. it seems that when we publish, we don't seem to see any fuss on that. So how are we getting away with it? What's going on? What is the problem? So let me just use a bit of an introduction here. What we do is we often measure the response of a pipeline, mostly its head, and we use it to find model parameter theta. This could be the physical parameter, could be the wave speed, whatever you want, or it could be the parameters of the leak location, could be the parameters of a blockage, what have you. So to a mathematician, these are the questions that need to be answered. Does using the head to infer parameter, does this problem even exist? Does the solution exist? And if it does, is it unique? And if it is unique, is it stable? Let me actually convince you that actually it does not exist, it's not unique, and it's not stable. So if it's none of those, it's called ill-posed. So how do we get away and solve these problems then? So first, why it doesn't exist? Here is the space parameters. This is where we have, for example, the space parameter. You could think there is wave speed. You could have all possible wave speed here. You have your Warhammer model and you map it forward, right? Or you get the response of the system. And this is the image space, therefore. So you take a wave speed, you map it forward. Another wave speed, you map it forward, and so on. Now, let's say then you turn around and say, I'm going to use my response here to estimate what my wave speed is. What you're going to do is you're going to do some measurement. When you measure, you're going to measure the head. The head is going to have error. The model have errors. They are never going to be in the same range. They are never going to be in the same image. Your head point is always going to be outside your image space. So therefore, now when you pose the response of the model equal to your measurement, they cannot be equal. This is your response, that's your measurement. They are not equal. It cannot exist in that sense. So now, of course, what do? Do we stop? What do we do? So we never are solving this problem. We pose it this way, but we don't solve it. What mathematicians do and what we do is we go around and say, well, we cannot solve the equality, but how about we change the problem? We solve the minimum problem. We minimize the distance instead. We say we can never get it to be equal, but surely we can make this as small as possible, the difference between them. So we minimize, and that's what's being here. So effectively, what mathematician will say is we take this point and we project it. We make projection, and then you send it backward to tell you what the wave speed is. Unfortunately, this solution is often non-unique, as I will show you. And we also have the problem of stability. Stability means if you have two measurements that are near one another, if you send them back and try to, for example, determine this parameter theta, what you get is that the values will be very, very different. And I'll show you, actually, we have a paper on that, or at least where we showed some of the results. So what mathematician, again, will do if you are in math, what they do to stabilize the problem, they put a condition on the norm also of theta, on the norm of your wave speed. This is where you will be using some of your prior knowledge. So if you get a wave speed of 10,000, you will throw it away immediately. Say, that doesn't make sense, and so on. So essentially, you put some norms there. Here is actually published in one of our earlier papers, the problem with uniqueness. So we are looking for leaks, and you can see we find this is the true leak location, and the blue is our model. We find two equivalent solutions. The only way we can get rid of that is we measure more. That means you get more equations. You get more equations, you reduce this problem of non-uniqueness. So that's how we got around it here. This is the problem of stability. We were actually determining wave speed, and we started to put a little bit of errors, and you can see after not very, very quickly, the wave speed actually jumps from from here to, from 300 to a value of 800. They're incorrect. The real value is actually somewhere here, about 400. So again, what we did here is the same trick, is we used more data, more equations, essentially. So what we used is more frequencies. Often people throw away the non-resonant frequency. We find that when you use resonant frequency, it gives you actually benefits by way of stabilizing the problem. We also, to save a bit of time, maybe this is another paper that we looked at a network, a leak in a network. So again, in this case, we find that the solution was also unstable, and the way to stabilize it was to look for which frequencies are more corrupt and remove them. This is a paper whereby we stabilized again the problem by removing the singular value. So you can always treat it again, because what we really solve at the end, you have a differential equation, but really when you write on the computer, it becomes an algebraic equation. That means you're dealing with matrices. So essentially you're doing singular value decomposition, and you just remove the small singular values, the ones that are of the order of the noise. So this also, therefore, to deal with this problem, you need to essentially deal with your noise very well. Just to finish up this part on inverse, I tried to show you something that you all should remember back from your first year or second year algebra. I don't know where you did your linear algebra. So you could use actually simple example to show a lot of these ideas of what happened. So let's say I give you a problem where you have a mapping again from the theta to an H space. And the mapping between them is with this matrix, which is 2, 2, 1, 1. All right. So essentially what you do is, this is the theta space and this is the measurement space. When you map, these two equations are redundant. So you're going to get 2 theta 1 plus 2 theta 2 is equal to H1, and you're going to get theta 1 plus theta 2 is, so essentially you have one equation, two unknowns, really. So it's going to be a bad mapping, and therefore it's going to give you trouble. And these are some of the games that we end up with most of the time. So what happened in this case is you start with a 2D space, okay, theta 1 and theta 2. What they teach you in linear algebra to look for a null space. That means what are the vectors that all map up to 0? And we find that all of these vectors, all the vectors parallel to this, they all map to 0. Right? In fact, the image of this whole plane becomes simply these blue lines. So you get a dimensional reduction. So what you can work with essentially is only this line. You lost information along the way. You cannot revive these. When you took your image, you took all of these good vectors, you send them to 0. They are dead. You cannot bring them back to life. That's one of the key problems for ill-posedness. So now this is your image, and things get a bit worse. What I just shown you earlier is that your data is not going to be in your range because you have errors. So your data is going to be off. So what you need to do is project, and that's what mathematicians would call the projection step. And then they need to do an inverse. But remember, this matrix is singular. So how do we invert? They need to create what's called the generalized inverse. Essentially, what they do is they say, I'm not interested in any of this. This gives me nothing. I'm just going to map between this line and this line. And that's where the mapping works. So we end up with multiplying two matrices. So if you don't want to do those, you could get this right in one shot by just doing the minimization. Now, the other thing that I like to, because we're still in models and you see more and more of these machine learning type models are, being published and coming to us. So why do we need these models? Well, I don't know, maybe I'm not really an expert in this, but of course we're doing some work on it. But just for those who don't know, it's basically a fancy data fitting. You have your inputs X, you have your outputs X. in the classical old way, we do linear regression directly between X and Y. And these type of model, you do a suite of linear regression, and you impart and then you put in what this activation function that introduces nonlinearity, and then you pass it through linear. So it's a suite of linear, nonlinear, linear, nonlinear until you get to the end. So it's a compounded. So essentially, this is a compounded operation. So you get your X, you get f of 1 of X, and then you get f of 2 of f of 1, and f of n minus 1, and so on. And it's supposed to be kind of rich and gets you all these things we want. However, these are, you can see, these are actually from math. I just got them this morning, 2022, 2023, and there is many. All of them complain. They say, oh my God, when I do these for wave problems, they suffer. And I'll show you a couple of examples. Why they suffer? They suffer from causality. Because when you fit data, it doesn't matter what you fit it is, if you're not careful. We know from waves if this is time and this is X. When you release a wave here, it follows the characteristics. And this one follows the characteristics. And you have this, what's called the region of influence. You should not, what happens here with this wave cannot influence this point. Right? It's just too early. And again, if you generate a wave here, this is the region of influence. These two waves only interact here. You cannot make data along this line interact. That's physically impossible. In the same way, you cannot get the future to influence the past. Okay, you need to respect causality, right? And so I'll show you a couple of examples. Here is example actually of causality. They're not a paper published by us. This is the exact solution, okay? And in here, where they take the whole data, so this is time, this is position, this is from their paper, and where they did machine learning, and this is what it learned. This is the solution it learned. It's quite bad. What they did, what occurred to them, and that's why they publish a paper, is saying, oh, the problem is actually causality, because this is the future. This is time. The future should not be fit together with the past. So what they did is they tried to fit delta t after delta t. So they use machine learning to learn this part. After they learn it, then they use this, becomes their new, and then they learn this new piece and so on. And then suddenly they get it back. So we really need to know need to go back and review our wave physics even more if we're gonna be basically using these tools. Remember, a lot of these are done by computer scientists. A lot of these codes, they are not necessarily thinking for us to do waves. Okay, so be careful when you do this. Discontinuities are also found to be a problem, like junctions of pipes. Discontinuities in wave speed. This is an example of a discontinuity in wave speed. Again, this is the ground truth. This is the prediction by neural networks. So when they take the difference, you can see the difference. If it is good, if the neural networks reproduce the ground truth, then the difference should be 0. It's not. Now, when they bring in the physics and they deal with the discontinuity and the wave speed, then you can see they get pretty good results. This is another thing also, be careful when you train, when to stop. So this is a paper showing you this example. They trained after 100 iteration. This is the data, and this is the trained model. They found that these machine learning tools, they actually learn the very low frequency first. So they learn your steady state, your quasi-steady state, and maybe your rigid water hammer, and then low frequency, and then to higher frequency. So you need to iterate more and more for them to learn it. It's very difficult for them. It's a bit like us, I think. We learn steady state first, and then quasi-steady, and so on, and then they learn it. So apparently machine learning are a bit human like us in many ways. Now, this is actually what our group played with this few years ago. If we use for 5 Hertz, we can use 5 layers, or I think it was 20 neurons to do this, and we get good fit for the solution. But when we increase the frequency, we had to increase the number of neurons. Why do you need to increase? Essentially, you see, if you have higher frequency, your function is going to be more complicated, highly nonlinear, and therefore you need more composition to be able to fit, because it's a piecewise. It's trying to fit everything as a piecewise. So you need more pieces into the game. You need more nonlinearity into it. Now, let me finish off by the last piece. Essentially, I really like this quote. If you, and this book, if you never had the chance, it's actually, you can download it from the internet, where he says, now full of confidence that we understand waves, both in theory and actual test, we fling open the laboratory door, stride to the edge of the cliff and look at the sea. Good grief. The real waves look nothing like the neat ones that march across the blackboard and orderly equations. These waves are disheveled, irregular, and moving in many directions. Should we slink back indoors to our reliable equation and brood over the inconsistency? Never. Instead, we must become outdoor wave researcher. It means being wet, salty, cold, and confused. What's the equivalent for us? I think where the equivalence here comes in is whenever we apply our models to real pipelines, the agreement, instead of the blackboard, think of the lab. We have really good agreement in the lab, but when we go outside, the agreement becomes quite poor in most cases. So what should we do? He's here advising them to go to the field. I think we must do the same. Spend more time in the field, because here is where we are. We are in a field where I don't believe it, I don't buy it, and I can argue with anyone here that we do have all the physics we know. And if we think we don't, it's because we didn't read enough. So we have all the physics there is to model, but we have small data and bad data, bad information. We know very little about our systems. We have all the math we need, all the physics we need, but our reality, which is our pipeline, is buried underground, is unknown. And lots of the pipes, we don't know even if they exist or not. We have experiences with those, even on our own campus here. Just to give you an example, a few years ago, they were looking for a leak. They hired a contractor, and they dug the ground to find the leak. They didn't find the pipe. So these maps are bad, and we can't really model a system that we know very, very little about. We know it's physics, though, and math pretty well. So what we really need to do, and I've been in this mission of convincing, water authorities, we need to develop, for any new system, we develop access points to pipe system to make them measurable. We convinced our university, we built a new campus in Guangzhou, and this campus has about now 57 access points. Okay, so any one of you should be welcome to go and use those access points and measure water quality. It's not just for us, really, for anybody who has any technology that want to go there and access the system to measure and to take sample to know more. We also encourage the development of a digital twin where you store. There is no reason nowadays not to keep very good data of our pipelines systems. We also suggest that you regularly collect and store passive data in this system, monitor the system, that is. These systems are important, expensive, and we should care about them. And we should actively, probe them. Let me think I have a time for an example to show you that when we do this, it's quite successful. This is a project we've done for Disney Hong Kong. In this case, they did monitor the system, the transient waves, for about a year. We got the data from them, and they know, because it's a sewage system and it's recently built, so they have good information about it. So you could actually go do very nice work in it. And when we did, it was not difficult to find that their data was showing they had problems with their air valves, and this is where they opened the chambers, and then they found it to be flooded. And we also, the data shows us that their pumping station was actually, one of the pumps was in bad shape. They did not believe it initially, but we went and put an accelerometer to it directly. So when it started and stopped, this is the type of signals. And when you put the spectrogram, you can see low frequency. These are the RPM of the pump, but you get all of these high frequency here that only has to do with the axles that was actually vibrating a lot. And they did eventually open that pump and found that, in fact, it was in bad shape. This is another nice, interesting example. Again, the data was collected by another company that collected this data. And interestingly, in this one, for every day, Bruno and Sylvia would remember this because we were in Hong Kong where the water supplies showed to us, and they were miffed as to why at 4 o'clock each day, there is a drop of about 10 meters of pressure for a few seconds and goes back up. So to us, this was a nice thing to do, the time reversal. So we apply time reversal to it because, again, you know enough about the system. So when you do time reversal, it's where the two waves met. I should have seen it here. Maybe you can play it again. So just watch these two. The waves were all superimposed here. And that's, in fact, what it turned out is this was a point where they had a fire hydrant. And on that fire hydrant, each day at 4 o'clock, one of these trucks comes in, opens the fire hydrant, fills up, and drives away. So there was really no leak. There was no theft. But it can, again, tells you. So, but the message here, this is in a complicated system. But because they know the information, they know the typology, they collected the data, we can do as good as the lab. So with that, I thank you very much, and I hope you enjoy, and I'm sure you'll enjoy the rest of the course.
Thank you a lot, Mohammed, for your very impressive talk. Few important ideas, good models, good data, and good physics to understand this phenomena, not only big data. Thank you. Any question for Professor Ghidawi? We have time for 1, 2 short questions. In any case, who is interested, you can send questions, and then I will provide to Professor Ghidawi, will answer separately. So time is very precious, so I give the word to David Ferras. Thank you again, Mohammed. Thank you very much.
Thank you.
Congratulations.
Thank you. Thanks, everyone.
Thank you very much, Bruno, and thank you very much, Mohammed, for this very insightful talk. Before we move forward, I would like to remind the participants to use the Q&A. So they can use the Q&A anytime during the talk, and then by the end of the talk, eventually, if we have time, we'll try to cover the questions, whether live or directly typing in the Q&A. Okay, so now it's my pleasure to introduce the next speaker, who is Professor Anton Slice, who has more than 40 years experience in both academia and industry in the fields of hydropower and dams. He worked for more than a decade in electrowatt engineering, now called AFRI. And after that, he worked as a full professor at the EPFL at the University Polytechnic of Lausanne, where he later on became honorary professor. I have the fortune to be one of his former PhD students, and I can tell he's a very devoted professor, always keen to support his students. And as you can see, even after retiring. So today, Professor Slice will give his talk on the challenges of transient flow modeling in complex hydraulic infrastructures for water and energy supply. So it is my pleasure to give the word to Professor Slice. Professor, the floor is yours. Thank you.
Thank you, David. I just share my screen. Okay, so can you see my screen already?
Yes, we can see your screen. Maybe if you can launch the presentation.
Is it okay now?
Perfect. Yes, you can go ahead. Thank you.
Okay, thank you very much, David. So it's a pleasure to see you again after some years when you did a PhD at EPFL. So I will be certainly a little bit less plunging into theory, but rather talk about challenges in practice of transient flow, modeling in complex hydraulic structures, infrastructure, especially for water and energy supply. So I will briefly give a little bit these challenges. Then I think if we are going into the modeling, which you will do with these models all the week, I think it's important to know a little bit what are the hydraulic structures, especially if we are talking of hydropower plants which have to be modeled. And therefore I will talk about the alignment of waterway systems of hydropower plants. Also talk a little bit about the purpose and types of lining, because this is important to know them in advance, because they influence, of course, the type of lining influences then the wave velocity. And of course, the mitigation measures which are normally used in practice are surge tank on chambers, just to give some typical oscillation. And finally, some ideas about monitoring of steel line pressure shafts by transient flow analysis. So complex hydraulic water infrastructures. In these infrastructures, of course, we have transient flow, which can occur during operation. But from my view, the huge challenge is that this potential transient flow, they have to be simulated with uncertainties already at the beginning of the project, before it is built. And of course, the project we heard already, typically we have water distribution networks, we have a cooling and heating system, we have pipelines, and of course, storage and pump storage hydroelectric power plants. When I was working in practice, before being called for a full professor at EPFL in 85 to 97, I was in a company where we had to use, or let's say we had to design water distribution networks, especially extension of such networks, but of course also quite complex hydropower plants. At that time, there were no, let's say, commercial, let's say, software to calculate water hammer, including, of course, mass oscillation. So at that time, the companies had some development funding, and we developed at that time our own software, which was called IAHR. If I say we, at the origin, there was a former professor of the IAHR in Delft, Nella Petri, and he was working at that time at Electrowat. He was mainly involved in the development of this IAHR, which we used 10 to 15 years until other, perhaps more user-friendly tools were available as commercial softwares. Okay, the model was based simply on method of characteristics. And just to tell you, when we had to calculate the extension of the Zurich water distribution network, so the calculation took about 1 week to calculate all the transient. Hydropower plants can be very complicated. You see here, in principle, a hydropower plant in Iceland, which was built a few years ago. We have, in principle, 2 reservoirs. You see the large reservoir, which is also on the picture, and we have a second reservoir. They are brought together by a head race tunnel into a common head race tunnel. Then there are some intakes on the way from smaller catchments. sorry, I just go back. And in principle, then the water goes down by 2 pressure shafts into the powerhouse, which has 2 times 3 turbines. Back again, so the problem, okay. And here you see, of course, we need a third shaft at that location, which at that time, that was a special third shaft because it was drilled by an access tunnel, which was going down by spiral. And that also learned us that it's important when you have a third shaft that you have to consider also the links. Due to the wave reflection in conventional models, very often the surge tank is just one element. Because there was a bifurcated head race tunnel, it was also very important to see that there could be a kind of oscillation which got into interaction with both. I would not say kind of a resonance, but it was very delicate, so we had to introduce in one of these tunnels, we had to introduce a throttle, which stopped, or let's say reduced the upflow during oscillation. Let's see, just forward, okay. Okay, so if we are looking at waterway system for storage and pumped storage power plants, so pressure waterway system consists of what I already mentioned. We have pressure tunnels, which have pressure shafts, we have penstocks, and then of course we have surge shafts and surge tanks. They are used for storage and pumped storage power plant. And the purpose, of course, is to limit head losses as well as leakage of these waterways. We call pressure tunnels if the tunnel has a slope less than 10%, and we speak of pressure shaft if they have a very high slope, higher than 10%. And just to say, we have about 500 power plants in Switzerland, and the total length of these tunnels, which of course I don't see, they are about 2,000 to 4,000 kilometers, so that can be very important. So of course, in hydropower plants, we have a preference, of course, that's clear, of pressurized flow. The reason is quite simple. We have a short reaction time of the system. Okay, when we talk of water hammer velocity about 1,000 meters, then of course we have a reaction of the system, which is when we change the discharge at the turbines quite fast. And of course, also important is that head losses are function of the instantaneous discharge. And finally, we can have longitudinal profiles as a zigzag, which you have going up, going down, which is needed if you are doing excavation by tunnels. You want to go always upwards. And therefore, if you have a pressurized system, this is in principle not a problem, unless, okay, the high locations of these tunnels should, of course, be below always the lowest water level overhead. If we are looking on the alignment of waterway systems of hydropower plants, if we have a short look on the historical development, if you see up here in the very beginning, we had in principle a head race tunnel, a pressure tunnel, and then a surge tank, and then mostly there was a kind of free penstock, open penstock. With time, there were technology developed which allowed, let's say, to excavate inclined, quite steep inclined pressure shaft. And more in principle, the open penstock was then in principle replaced by an inclined pressure shaft. And then with time, also large underground cavern could be excavated. So in principle, the open powerhouse, which was at the beginning of the last century very often used, was then replaced by an underground powerhouse. And then in certain conditions, like for example in Scandinavia, where you have high level plains going down to fjord, then such a system like a very short vertical pressure shaft was developed going down to the powerhouse and then followed by a tail water tunnel. And even in Norway, in some arrangement, they used a very short direct connection to the underground powerhouse. And then, of course, since there was not a possibility to have a surge tank which goes to the open surface, air cushion surge tanks were developed. Today, there is a tendency to use vertical pressure shafts, as you see here, which prolongation towards the surface are then directly corresponding to the surge tank. And then we have a higher, lower pressure tunnel, which goes to can be an open or an underground powerhouse. The advantage of vertical pressure shafts is that because of the high rock overburden, we can avoid steel lining, which very often is very expensive. We have in the world at the moment a kind of a renaissance of pumped storage power plants. So there is a tendency of alignment of these pumped storage power plants. It is wished that, let's say, the underground powerhouse is quite close to the upper reservoir, which is then connected with a very short head raise tunnel and the vertical pressure shaft to that powerhouse, and then a longer tail raise tunnel to the lower reservoir. Also here, if with such a configuration, this pressure shaft can be led without steel liner, which can reduce cost in certain project to $200 or even more million. But of course, a very short stretch just close to the powerhouse has to be steel lined. Then the tail raise tunnel, depending on its length, surge tank here is needed or not. So at the beginning of such a project, we have to know what are the type of linings, because they influence, of course, the wave velocity if we are doing some simulation in advance for the project. So I go really briefly through these linings. So lining, of course, why we do have linings, because we want to have a tight tunnel as much as possible, limit the water losses. We want to sustain the groundwater table around in the rock mass. We want to limit head losses. And of course, we want to ensure the long-term stability of the pressure tunnel, also minimize the maintenance and guarantee the mechanical and chemical integrity of the rock mass. There are some rock masses who can be change their behavior with water, underwater access, like anhydrite, which then can transfer to gypsum, which then has a huge amount of, let's say, expansion, which then can endanger the tunnel. And finally, also to guarantee the stability of the tunnel during operation. Unlined pressure tunnel exists. The lining can be omitted if the excavator profile is stable during excavation. The rock has a very low permeability. The groundwater conditions are favorable, and the rock matrix is not susceptible to water action, as I already said. For example, if we have anhydrite, and of course, no washing out of fine materials in rock joints. With variation, for example, oscillation in surge tank can be dangerous in washing out of such material, which then creates in a longer time can create severe rock falls in tunnel. Okay, here you just see the roughness which we have typically in such tunnel. Of course, if they are excavated by TBM, they are much more smoother than excavated by drill and blast. So here you just see an example of on the left of unlined tunnel. You see there is very often there is put a concrete element on the invert, which allows evacuation of excavation material by trains, typically electric trains in this tunnel, very smoothly. So the rails can be fixed on a good concrete elements, but also for, let's say, maintenance during operation, and also evacuating water during construction. Such invert element are today systematically placed even in unlined tunnels. Then we have shotcrete linings, which are just a kind of a support measure that we don't have rock falls during operation. You see there, typically it's up to the 15 centimeter of this shotcrete. Normally there is a wire mesh in it. And of course, let's say the roughness is quite high of such shotcrete, especially in drill and blast tunnel. It can be smoothened a little bit if the shotcrete is smoothened by hand, which is very expensive and normally not done. Then we have unreinforced concrete linings. You see here values of thickness. The purpose of this lining is typically to reduce head losses, because under internal pressure the lining normally crack and they cannot control water losses. So here just two examples of such concrete linings. If we have to limit water losses, we have to reinforce this concrete lining. Normally a reinforcement has to be used with quite small steel bar, not spaced too much, because the purpose is to limit crack widths to something like 0.1 to 0.3 millimeter, so that we don't have the danger of washing out of joint fillings, which can, with time, produce a failure, a dangerous failure of the tunnel. So here is just also two examples of such reinforced concrete lining. There, sometimes in the past, there was used a kind of a pre-stressed concrete lining to make a pre-stressing of the concrete in order that due to internal water pressure, it will not crack. So thus, therefore, being almost impermeable. And this passive pre-stressing was made by injection pipes, which were in principle placed directly on the excavation, and then the concrete lining was poured, and through these pipes with pumps, in principle, cement grout combined with sand, fine sand, was then pressed behind the concrete lining, as you see here, in order to get a pre-stressing which is higher than the tensile stresses which occurs in the concrete lining under internal water pressure. So that is quite efficient measure to avoid cracking of concrete linings. If the rock is very permeable but has a very good strength, there can be also placed some PVC sheeting, geomembrane, which are protected by an inner concrete ring, because when the tunnel is emptied, otherwise this geomembrane would buckle, respectively would just push inside the tunnel. Therefore, it has to be protected with an inner concrete ring. So here, just an example before placing then the inner concrete lining. Here also an example. And finally, what we find in the pressure shafts, which have very high pressures and perhaps not enough overburden. So we have the steel liners, which are embedded by backfill concrete towards the original rock. So, okay, when it comes to transient calculation, and especially also surge tank oscillation, we have to consider when we are estimating the wave velocity, or just copy paste some formulas here. You see pipe and conduits, this is steel, and then is diameter of the pipe, the thickness of the pipe, then this is the elastic modulus of the pipe material, for example, is the pipe material, sorry, this is the modulus of the water itself. And here we have on-line tunnel, then we have a contribution of the rock, and then a little bit more complicated, a line tunnel in rock. You see the formulas get a little bit more complicated. And finally, a steel line tunnel embedded in concrete and rock, where you see that the contribution of the steel liner, of the concrete, and of the rock is implemented. In practice, of course, we have to know let's say, the deformability of rock and concrete in advance to estimate in these wave velocities in different parts of the head race and tail race tunnel. And that, of course, is quite challenging because we have to do some assumption under uncertainties. Then, of course, everybody knows when we do a transient calculation in hydropower plants, okay, we are interested to know the water hammer. Then we know if the water hammer, the system is very long, the water hammer gets higher and higher, and therefore normally we need a surge tank to protect the head race tunnel against water hammer. So surge tanks are quite important structures, which also have to be designed in a very early stage of design. So it's very often challenging because the excavation is not yet done. So sometimes we do not know all the characteristics of the linings inside. So we have to do also studies with uncertainties. That means we have to do a lot of sensibility analysis to know a little bit where we are. The main purpose of surge tanks, I think that's nothing new for you. So it should reduce the amplitude of pressure fluctuation caused by water hammer. And the water hammer, of course, is caused by a turbine or a pump operation, change in flow rate. The water hammer is reflected at the first free water surface, which can be forced to be as much as close to the power plant by such a surge tank. And as I already said, the water hammer depends on the system length. The purpose is to improve turbine control characteristic. And a surge tank has also a kind of a water storage, which helps fluid acceleration and deceleration in the penstock or in the pressure shaft. So this is dampened force and link by the storage in the surge tank and pressure fluctuation in the system. I'm now talking of water hammer are reduced. So when we have a change in turbine or pump flow, that is a change in the kinetic energy in the head race tunnel. So my colleague has mentioned it before by a number of cars. If the tunnel is very long, so that can be 10 kilometers of heavy trucks which are running down towards the powerhouse. So there is a huge mass which has important inertia. And the variation in energy releases or absorbs a quantity of energy that the surge chamber must absorb, supply. So it does it by raising of its water level or lowering of its water level. That means by a mass oscillation. The period of this mass oscillation wave generally lasts a few minutes. So it's quite a slow oscillation, which increases pressure periodically in the head race tunnel and lower it again. The period of a water hammer wave, of course, on the other hand, is in the order of seconds, depending on the length of the system. Consequently, a pressure measurement on the penstock shows two waves of very different origins. So if we measured just at the powerhouse, we have a wave of pressure resulting from the water hammer, which is very short and abrupt with high propagation speed. And we measure then also a mass oscillation, which occurs in the search tank, which can be compared to the oscillation characteristic of U2 with low propagation speeds. So the design criteria for search tanks, which of course is based on the use of transient models, water hammer models, combined also of course with mass oscillation. The search tank must be large enough and high enough to ensure that the water never overflows. The search tank must allow the turbines or pumps to open or stop at any time without emptying, so that no air enters into the penstock, which can create huge troubles at the turbines. And the cross-sectional area of the search tank must be greater than the limit value that guarantees a stable control of hydraulic machinery. So if you are looking at search tanks, they are in principle vertical cylinder excavated in the rock with wider diameter, less wider diameter. Some can have an overflow, controlled overflow, as it is shown in these examples. Then if the oscillation are too high, then we can, the upward oscillation can be limited with chambers, which are widenings as you see here, down search with lower chambers. Here chambers which can have overflow, chamber lower with a controlled overflow on the top. And here upper and lower chambers in different configuration. Here again an upper chamber with overflow. So there is a lot of possibilities which are used in practice depending on the local, let's say, constraints. So then we have so-called differential search tanks and search tanks with orifices. Search tank with orifice is just a kind of a throttle at the entrance to the search tank, as we see here, or kind of perforated plates, large plates. Then differential search tanks mean that we have different parts of the search tank where the water goes up and then encounters, flows down to the flow coming up in the middle section. So these are differential search tanks, which you see also here. There are a lot of different possibilities, also differential search tank. That means, for example, the upper chamber, the water doesn't go directly in, but has to go over it. And then there is a differential behavior here in this upper tank, and also here with such a wall differential behavior that it doesn't fill very fast and doesn't empty too fast, for example, this lower chamber. Then, okay, oscillation in a simple search tank. This is not from theoretical point of view, is the mass oscillation is not very complicated. I would say at the beginning of any project, we have to have a very rough estimation first, how big the search tank has to be so that we can see where we can place it. So here is, for example, a very approximative kind of empirical equation which gives the maximum upsurge compared to the initial flow velocity in the head race tunnel, depending on its length, on its section. This is the section of the head race tunnel, and then we have the section of the search tank, which is this big A, or and then the influence of the head losses, of course, in the system. So if we have a look a little bit on dimensional analysis of typical maneuvers for search tanks, so sudden opening and sudden closing. So this graph gives the up and down surge as non-dimensional numbers influenced by the length of the head race tunnel, section of the head race tunnel, and section of the search tank. So this is the dimensionalization of this value. Then we have for a sudden, we have then the adimensional time, as we see here, and we have also an adimensional head loss in the tunnel, and we see, okay, these are the typical oscillation if there is no friction, and the higher the friction is, the more this oscillation is dampened. As you can see, here is the opening, here is the closing below. And here, this is in principle the graph which gives the minimum downside, the minimum level in the surge tank and the maximum level depending on the head losses in this dimensional form. Then, of course, consecutive opening. So we have here an opening, then which is then followed in the most unfortunable time, as I would say. So we have then a superposition of the oscillation which is created by the closing. And here is the same opening by superposition of a closing. Here again, which gives then the minimum and the maximum level in the surge tank. And finally, of course, that was a very fast, instantaneous closing and opening, which never happens in practice. So we have normally a gradual opening and closing of the machinery, which is then also with an adimensional time. As you see here, we have for different roughness in the surge tank, we have then, and for this closing time, dimensional, we have then this maximum and minimum upsurge. So surge tanks with expansions and lateral chambers. The purpose of expansion and lateral chambers are to limit the oscillation. We have the following possibilities. We can widen the surge tank shaft over its own length, or we can, as I already showed you in pictures before, we can have lateral chambers or galleries, straight or curved, and we can have flow-through chambers or galleries during oscillation, and we can also have surface basin upper extensions. Surge tanks with expansions, they may have stability problems for medium head power plants. They are less efficient and economical for relatively low heads. To mitigate these disadvantages can be done with an orifice at the foot of the surge tank. An orifice, of course, is an additional head loss. In the case of closure, there is a low back pressure at the start with a rapid growth, and in the case of opening, is a negative pressure accelerates movement in the gallery. So surge tanks with orifice, they have the advantage to facilitate the operation of the machinery. But of course, due to the orifice, some part of the water hammer is transmitted to the head race tunnel. If this part is small, normally it can be accepted. So differential surge tanks, I already mentioned them. The typical solution is that Johnson. So we have an inner part of the surge tank where the water goes very fast up. And here is an orifice inlet to the lateral parts. It goes up slowly. Then, of course, here is then an overtopping, which then stops by the plunging energy, this upcoming water from the outer side. So this, and then this the opposite going down. We have water storage, which comes then slowly and also hinders the downsurge downwards in such a way. These are upper expansions with differential behavior. As already said, the water overtops here very fast. And then when it goes down, there is a kind of outflow, which hinders also the downsurge or makes it slowly the downsurge. Finally, stability condition. Okay, that's very simple what I present here. Then, of course, today we have much more advanced theories, but Thoma gave a stability condition where criteria for the surface of the surge tank, which has to be higher than according to this formula, which is depending on the section of the tail race tunnel, which is depending on the flow velocity in the tunnel, and then also depending on the head losses in the system. This Thoma criteria was developed mainly for head race tunnels, which here this part is very long compared to the pressure shaft. So if the pressure shaft is quite long, or let's say if the head race tunnel is quite short, it has to be corrected against the criteria which was introduced once by Evangelisti. So if we are calculating water hammer and surge tank oscillation, the question is always which type of, let's say, design criteria has to be used. So if we have shutdown of turbines and opening of turbines, the question is with what we combine them, which head losses we combine them, because we do not know from the very beginning which are the really precise head losses, but we have a kind of a range between minimum optimistic, optimum, maximum pessimistic, and so on, average. And you see, it's clear if we have a shutdown of turbines, we have to combine with optimistic values, which give and with the maximum minimum reservoir level, which gives normally then the highest down surge in the surge tank, and so on. If we have a combined opening and reopening, then of course we work with average values. If we have pump storage, we have closing of turbines, starting of pumping, closing of pumps, starting of turbines, and so on. And you see we combine them with these load cases with either optimistic, pessimistic, or average values. Now, just to finish, I would like to give a kind of a practical application of transient flow analysis, where I had the chance to have a bright, let's say, PhD student, which finished his PhD before David. He came after. He was also very bright. And the idea is, in principle, monitoring of such high pressure tunnels or pressure shafts. We would like to know if somebody happens in the tunnel. So if we have suddenly a weak zone, so a cracking of the lining or deterioration of the lining, and we know that the pressure wave in a pipe is influenced by the section of the pipe, of course, by the wave speed. And if we have a change of behavior, then of course the wave speed will also change. So that means the wave speed depends on the stiffness of the liner or the liner support, which can be concrete rock or a steel liner. And if something happens in this liner, in principle, the wave speed is changed, or we notice a wave change. So we, in principle, okay, that is perhaps not a hypothesis, that is quite clear, but we wanted to know how we can detect, let's say, weak reaches in a pipe. And the idea was, we produced the source of a water hammer at the beginning of a pipe with a very fast closing valve, and then we have here the reservoir, and we measured at two locations, in principle, the signals of the water hammer. So the wave speed, in principle, and the wave attenuation will be changed if there is a weak reach in this pipe. So the general strategy for, if we use that concept, for example, for streamlined pressure tunnels, we can generate at the lower end of the pressure shaft at transient. In principle, you don't have to generate it. It is always generated if there is a change of flow at the turbines or at the pumps. Then we compare wave speed and wave attenuation at the lower end and the upper end of these pressure shafts. And if there is a change, we would like to find where this change is, how much it is, and then if there is we find it how much it is, then we can go to the last, which is then a detection of visual detection and leak detection. So our configuration we used is in principle a pipe. You see it here. And the pipe, we have here the valve. And the pipe in principle, okay, go back again. We had the possibility to include in this pipe reaches with different material. So we used, the pipe was, the basic material of the pipe was steel. So in some reaches we introduced an aluminium part, a different location, as you see here, longer and shorter. And to have a larger difference in deformability, we introduced in some parts a PVC stretch of pipe at different location. What we did, we measured at, in principle, the pressure results at location upstream and downstream. And you see here the typical signal. The valve was closed very, very fast, less than 0.3 seconds, as you see here, from this region going from green. This is the region of the valve closure. So this is the pressure at the location 1 and the pressure at the location 2. The same was done with geophones at the location 1 and 2. So here 2 typical analysis windows. And then to compare the signals at the 2 locations, we used all these mathematical processor tools. I do not mention them all in detail. So for example, the wave speed, we could estimate from the steep wave front transients. So we had 3 different methods: time separating the pressure peaks, time separating the toe of the wave front, and the cross correlation in time lag, which allowed us to get the mean wave velocity. And you see here all the configuration we tested. So this is the steel pipe. This is the reference configuration, then a steel pipe with part of aluminium introduced. We see it here. These are the aluminium parts, and these are then the parts introduced with PVC. And what we can see, of course, if we compare steel with aluminium, the difference is not so high. So the scatter is quite high. It is perhaps a little bit more difficult to have, let's say, a concluding measurement of the water hammer wave speed. However, if we have something which is relatively weak compared to steel, as this PVC, then we can clearly detect, in principle, the water hammer wave speed. So here the same from the using geophones and pressure. So that was the correlation, because very often it's easier to measure, let's say, water hammer, or let's say the pressure by geophones, and then with pressure sensors. Then another point is the wave attenuation, estimated from the steep wave front transient. So this is in principle here, and this allowed us also to obtain a clear signal if there is a quite weak stretch like this PVC part of the pipe. And we estimated also the wave speed from the flow stoppage at the valve, according this approach, quantifying the input of the energy by the valve, defining the pressure signature to the flow along the pipe, and then estimating the travel time by cross correlation, which then give also, again, the wave speed, as you can see here. So the answer to the question when, it's clear the wavefront speed and the wave attenuation are good indicators for detecting significant local drop in the stiffness of the pipe or shaft wall, so that we could, in principle, say. Then the other question is if we can predict where it is, and okay, if we have determined this mean speed, then of course pressure wave speed, then we can also, when we know this time lag, we can also in principle determine the location of this weak reach if we know this time, which we can see by the signal analysis. So this was done by comparing, for example, if we have the FFT, by comparing, let's say, these maximum frequencies, where theoretically the frequency is the wave speed divided by 2 times the length. And this allowed us, by this comparison of these peaks, in principle, to have this fundamental estimated frequency. So, and then by wavelet decomposition, we can then, by these reflection peaks, we can get then this delta T, which allows us then, in principle, to answer the question where. And what is interesting, this is now the result. So if we have steel and PVC pipes, different location, we see that in principle we have a quite good prediction of the real and estimated distances of the upstream boundary of the weak reach. You see here we have an error of some percent. You see it here, 4.5%, 3%, here 1%. So it's quite a good prediction. Also the downstream part or reach of this weak reach. So also here we have a quite a good prediction of this with this water hammer wave velocity and analysis. So also here again, that's the center of the weak reach, also with quite good precision can be detected, as you see here, a few percent of uncertainties. And finally, the detection of the severity. So we want to know what is the, let's say, the estimated stiffness here of this reach, and this can be obtained also from the wave analysis, wave speed analysis in this weak reach, or influenced by this weak reach by these formulas. Just to finish, we applied in principle for the first time this at the real pumped storage power plant in Switzerland, which is in Grimsel. Here is the lower basin, the upper basin. It's a steel line pressure shaft, so we introduced the measurement just upstream of the powerhouse and downstream of the surge tank. And you see here these two measurement locations. The powerhouse directly with geophones, but also pressure sensors. Then with pressure histories, when the turbine are opening, the pumps are opening, so we can measure the water pressure at these two locations. We can then do FFT of pressure. We see the peaks, the hertz of the peaks. So here again, this location of the pressure sensor here, just upstream of the turbines, pump turbines, and at that location. And what is the usage of that? We can compare by a kind of a statistical quality control. We can compare wave speed and wave attenuation with time, with so-called 3 sigma criterion. So we compare the mean values with the upper limit and the lower limit. And finally, for the power plant, we can make such a graph of wave speed. We have a lower limit and an upper limit at the beginning before something happens. And then we can control with time if suddenly we get a weak reach somewhere. Then, in principle, we have to go with the procedure I explained you before, and make a detailed analysis of the signals of the water hammer, and then to predict where it could be, how much it could be before doing a visual inspection, which normally takes time, which needs a shutdown of the hydropower plant. So this helps to detect very early if something happens, and then to avoid visual checks all the time. So that was what I wanted to present you. So I was a little bit less, let's say, plunging into the theory I said. So in principle, I showed you how important it is, the transient analysis, and what are the challenges for large complex hydropower plants. So we have really to know what are the type of linings, what are the wave velocities in these different parts of the tunnels. We have to do assumption at the very beginning of the design with a certain uncertainty. So sensibility for the different assumption is very important. And then, of course, we have to know what are the structural implications. We have to know how the surge tanks option looks. That they are modeled correctly in this quite sophisticated water hammer model. So it's important that we model these structural elements as close to the nature as possible. And finally, I also showed you that with water hammer wave analysis, speed and attenuation, we can predict by monitoring, which is remote, with time if there is a problem somewhere in a pressure shaft, because pressure shaft failure can produce huge damages, as we have experienced for certain hydropower plants, and such a monitoring is very, very beneficial. So I think that's what I wanted to present you. Thank you very much for your attention, and perhaps you have questions to me.
Thank you, Professor, for this very interesting talk. Also for providing this historical overview on the evolution of hydropower schemes before moving to the technical details of engineering design, and also for providing this example from Hackem's work concerning a water hammer test and monitoring in a real hydropower scheme, which is quite unique. Okay, so we have a question in the Q&A. It comes from Sunik. The question is, are there any obstacles when installing passive pre-stressed concrete lining using the TWAG method? What obstacles usually occur?
I would say there is, okay, there is an obstacle, if you can say obstacle, it's a patented method. So you have to get this permission, but otherwise there are not really obstacles. Of course, it's a little bit hindering. It takes time to do the grouting of this lining, but very often it can be done quite fast after the concrete has been poured in the tunnel. So normally it doesn't hinder really the first putting into operation of the power plant. Of course, this method can be used only if the rock mass is able to take the pre-stressing pressure by the grout pressure behind the lining. So the certain minimum cover of the rock mass is needed. So a certain amount of natural stresses in the rock mass is needed in order that this method can be applied. Then it has been applied, for example, quite recently in a large tunnel of power plant in downstream of the Niagara Falls with a very large diameter. If I remember, it was more than 12 meters. And this worked very well. Normally, the amount, you cannot measure the stress in the lining during pre-stressing. What is done, of course, you measure the deformation of the lining, which then can be translated to stresses in the lining. And this measurement of the lining today is done by laser. So there is a laser scanning. And of course, the lining does not deform completely circular. So very often it's a kind of an elliptical deformation, which creates then also kind of a bending, which of course has to be limited. I don't know if this answered the question more or less.
I believe so. Yes. So, and a second question came up. Thank you very much for your presentation. I have one question. If we compare attenuation ratio between simple restricted orifice, differential, inclined source tank, and source tank with expansion chamber of a system, which source tank will provide good attenuation of source wave?
That depends on the case. So this different. Okay, there are some rules, some experience, what is the most promising type of search tank. But what is done if you have your very nice simulation tool, water hammer and search tank, okay, you try. First option, second option, third options to find the most best option. Of course, this is then a close discussion between those who are modeling and those who are more responsible for the construction. So then it's a trade-off, what is most economical, what is most easily to build, what is most easily to build fast. So this is then a very nice interaction between the modeler and those who are rather doing the structural design. And it's important that they work together from the very beginning.
Indeed, yeah, and it's impressive the different types of search tanks that there are in the catalog. No, there is high diversity, and this is an indication that it's quite a case-dependent problem. No, that's why we need the hydraulic modeler trying to describe each of the scenarios, testing the different options. Great. So yeah, I think these are all the questions we had. And I see that looking at the program, we are right now in what we should be a coffee break. So let's have a 5 minutes break, and then we'll resume the session at 2 o'clock with Jose Driasola as chairman. Okay, so if any other question pops up, feel free to write it down in the Q&A, and then we'll try to answer later on through directly typing the answer in the Q&A. Said that, let's have this 5 minutes break, and we start at 2 o'clock Central European time. See you in a bit. Thank you.
Hello, everyone. Good morning, good afternoon, or good evening, depending where you are. My name is Jose Ayasola, and I will be chairing this session together with Jose Vasconcelos. And I would like to kick off this session introducing the speakers. I'm honored to present Professor Brian Carney. And he graduated from the University of British Columbia in 1980 and got his PhD in 1984. He has been at the University of Toronto since 1987 and active in the consulting company Hydratech throughout that time. He has almost 40 years of experience in providing professional services in a wide range of fluid systems, including water, wastewater, storm, oil, gas, and jet fuel. He has spoken and written widely on different subjects related to water resources, energy issues, and hydrology. And he has been awarded a number of many, I would say, teaching and research awards. Together with Professor Carney, we have Brian Singh. Brian is a senior hydraulic specialist at Hydratech with almost 20 years of experience in water and wastewater industry. He received his bachelor and master's degree in civil engineering at the University of Toronto, and he's a licensed professional engineer in the province of Ontario in Canada. So Brian has worked in many hydraulic related projects in Ontario, across Canada, and internationally in many subjects, including transient analysis, field monitoring, etc. So he's an expert in this in hydraulic modeling and numerical transient modeling and design and optimization of surge protection and hydraulic field investigations. So many thanks to both of you. And for the audience, please don't forget writing your questions and comments in the chat during the presentation. So with that, Professor Carney, please go ahead.
Thank you very much for that introduction, and great to be here and to be present with people in all sorts of different time zones and backgrounds. Brian Singh is going to be managing the screen, and I'm going to be walking through the first part, and then Brian will jump into the other parts. Unlike Mohammed's first presentation, which had some mathematical components, we're going to try to give you a really high-level view. I'm going to sort of be the drone view of try to give you an overview. And Brian Singh will jump in and give some of the on-ground challenges with respect to using simulation software. And as Anton Schleister did so well, his presentation was highly influenced by a hydroelectric context. Our influences are strongly municipal systems of leading with water transmission and distribution systems. And yet we've done other kinds of systems as well, but that will be the primary focus. So Brian, let's jump in. One of the key things that I think sometimes fluid mechanics books don't do, Mohammed sort of made that point with respect to some of them as well, is they can be preoccupied with the issue of capacity. That is, can we get water to meet the required demands and flows at an adequate pressure and at a reasonable price? And the issue of economics and the deployment of resources is always background to that question. But one of the things that happens in that formulation, of course, is that you start thinking about so-called minor losses that happen at certain appurtenances and valves along the way. But we really try to resist that. We think of local losses in that context because the local losses dominate under this next set of considerations, which is how do we take control of what's happening so that we get not what's theoretically possible, but what in fact what we need. And that's really the issue of control and pressure and flow control to actually deliver through the system what we want. And requiring safe control of that is really what is the key thing of what's happening next, how what needs to happen in between. And we have to control the outcome. That is, we have to get where we want to go, but we also have to control how we get there. And that's really the main issue with respect to transient protection. And of course, a good transient protection does inform the design at the beginning, but it's sort of secondary to the primary considerations of capacity. I'm going to use a little bit of an extended analogy here for just a little bit with respect to a car, dealing with really the magnitude and timing of momentum changes. Mohammed again set the framework very well, saying that what matters is this delta T, and that's what invokes compressibility. But I'm going to give you a little bit of a nuance on that. If you consider a car, imagine a car or even a bus with passengers or a train, and it's traveling at considerable speed, and it needs to stop. Pretty basic considerations of ones that we've almost all had considerable experience with. The easiest thing that we can do, we do it with airplanes, is let the vehicle coast. In order to do that, we need lots of time and lots of distance in order to be able to actuate that change. The next thing that we can do, we can brake lightly. That is, we feather our brakes. We try to conserve the brakes as much as possible, keep things smooth, but with brakes, we can make those changes in a faster time over a shorter distance. And the passengers may hardly even notice the change if we do it well enough. They can continue to drink their coffee or their other activities without any trouble. But sometimes there's a need to brake hard. There's a sudden obstacle. There's something that needs to be done fairly quickly. And if we do that, we can use our brakes and we can brake even faster over a shorter period of time. But if we have to do that, the passengers might complain about what we're doing, and we may well spill their drinks or other disruptions in the system. The worst thing that can happen, of course, is we can crash. And if we crash, that can take place over a very short period of time. We can hit a solid obstacle or a tree or some other obstacle in the middle of the road, and we need little distance or time to do that. But of course, it's highly dangerous. It's likely to be disruptive and likely to be costly. And the crucial question is, can we do an emergency invocation of extra time, build a cushion in so that we have an airbag deceleration rather than a body bag at the end? Sort of the play on words at the end of this process, but it's anything but a playful operation. Accidents are horrible. Now, the reality, of course, we have to design airbags to take into account the possibility that there could be a collision. But think about compressibility in this context. Compressibility is a last-ditch effort to deal with cushioning momentum changes. The real challenge here is momentum change, and Mohammed said that very well. And the help for that is, well, sometimes we have to use compressibility because we're stuck. And really what Brian and I are going to argue is that this preoccupation that we have with wave transformations really is what we have to invoke only at the end of the process. If we have a well-protected system, we have no need to use compressibility. You know, if we can brake hard or brake lightly or coast, then compressibility never comes into the picture. And I find that really a helpful image with respect to this design question. We seem to have gone backwards there, Brian, and said, there we go. Yeah, so the key to good transitional controls is not so much to avoid water hammer, but to avoid rapid changes in momentum. And to do that, we're adjusting the timing. There's this marvelous quote that I just happened to stumble on the weekend by Mary Shelley in her classic book, Frankenstein. She says, nothing is so painful to the human mind as a great and sudden change. And I would say nothing is as dangerous to our pressurized conveyance systems as great and sudden changes of momentum. And if we don't control them, we end up with a monster. And the monster is we have to tame this. And so really fundamentally these transient control or controlling these changes to preserve systems so they continue to do their job. And again, the thing that's so important to remember is that most of the systems that we design in this way are capitally very expensive and may last for a very long time. And so we need to do this well. But changes in one system are never really everywhere all at once. Instantaneous changes is really something that very rarely or never happens at the macro scale. And one of the things I'd encourage you to do is to try substituting L over A into the expression that we're seeing for the so-called acceleration head, which I consider to be the key parameter or metric of the speed of changes. And if you simply take an incompressible model but put a finite amount of time on the change, in other words, to substitute L over A for dt, that's another way you can get to Joukowsky. And what practically matters then is really how dramatic are the initiated changes in the flow and pressure. And sometimes we have to deal with the possibility of collision, so we properly design our the front ends of our cars to collapse and compress properly, and then so the air valves deploy and work properly. But again, the next question is how far and how fast they do travel in the connected system. And of course, how does that connected system respond to it? Are there a sequence of cascading events that propagate through the system? And really that's what our goal in any simulation program is to predict, is to try to anticipate the magnitude, the duration, and the propagation and the response of the system to these changes so that we can anticipate the worst outcomes before they happen. I'm having great fun with my 9-year-old granddaughter and teaching her math. And one of the things I just constantly remind her of, we do math not because we're nerds and not because we want to escape from the regular world, but we do math because it's the best game in town we have for making predictions of something before we do it. Transients are acoustic waves. When you have to invoke those compressibility effects, you get that finite propagation. And as acoustic waves, I like to think of them as a conversation fundamentally between the boundaries of the system. The boundaries are what really induces the change and invokes different aspects of the change in the system. And the active participants or the arguments are what happens between valves and turbo machines, which are really our primary control device, which initiate and react to the changes. And it's not really the conveyance system that determines the nature, the character of the response. It's normally the active devices in the system that are initiating and responding to the change. And sometimes the conveyance system does intrude with things like bursts or with a change in phase, like a steam event or a freezing event. But normally those things, themselves are offload initiated by the boundary devices, and they're the thing that determine the character. So be preoccupied with the devices that change, because they're the things that both affect, control change, and sometimes disrupt it. The devices in the conveyance system can escalate or moderate the intensity of the acoustic conversation that's taking place. We just heard a fair bit of detail about surge tanks. Surge tanks really are changing compressibility effects back into gravity effects, where they're much more benign and much less dramatic. But the key issues are, in what ways are the changes going to take place, and who is responsible for that conversation? I love in the midst of a world that seems to have lost diplomacy to think that really, what our transient protection is to be diplomatic about the change. It's to do it more slowly, to communicate more effectively. But we're ultimately asking the question of what pressure can do in the system, because really it's pressure that's the most destructive force. And so the question here is really, is the system strong enough to withstand whatever's the residual effect that we can't economically accommodate by changing the conversation? Again, I don't know what your conception of this is, but when we're invoking compressibility, when we're bringing about those changes, the message that's sent is really a straightforward one. And to me, it comes from that really fascinating question, which I love to ask undergraduates or preoccupied with steady state, is how on earth does one end of a pipe know what the other end of the pipe is doing? And if you think about that, there's no direct communication that's possible. There's no magic that takes place. There's no conspiracy that's part of that. What happens is the pipe breathes, right? That there's an imbalance. And the imbalance is really of two basic forms, that you have less water into the pipe because of reduction in inflow or an increase in outflow, which is too little water, which causes a pressure decrease, or too much water that's associated with typically a increase in inflow or a reduction in outflow, and that's going to give you a pressure increase. And there should never be, in a practical context, much ambiguity about what sign of delta H we're talking about, or delta P. Really, we're talking about that basic consideration of how do the physics dictate how storage is going to be brought about by what happens at the end of the pipe. And that is water hammer. Water hammer is that communication that seeks to coordinate what happens between the ends of the pipe. It's a call for a system to get with a new program, to assess what it's doing and bring about a conversation of change and adjustment. And really, when you're watching a simulation, when you're seeing it animated, which is so interesting, it's extremely interesting to think of this as, okay, the valve is closing, so the reservoir responds, that addresses the imbalance, but creates new problems. And of course, where the greatest challenges happen are often when there's phase change, when we're intruding or extruding air or creating or destroying water vapor in a typical water system. And the picture to me is so universal for virtually any transient event that takes place in any system, is to ask that question is, what does the system do with any imbalance in coordination between inflows and outflows? When it happens in a bank account and you have more deposits than withdrawals, the bank balance goes up, usually a desirable thing. If we have greater expenditures than income, then our balance goes down and we need to watch ourselves. It happens with weight, it happens with biological energy, it happens with respect to the rotating speed of a turbo machine, and it happens in a pipe. We have equilibrium, which is balance, which is brought about by a rather subtle conversation that takes place between inflows and outflows and generates a lot of noise in the system. Or we have those two events that I mentioned of things that generate increases in pressure, increases in storage, which are reducing the outflow or increasing the inflow, and the things that result in pressure decreases of really increased outflow, like a burst, like opening a valve, like load acceptance in a turbine, and the things that reduce the inflow, like a power failure in a pump. And it strikes me that under most circumstances, the things that initiate events that are most consequential are often those negative pressure events. They're often the things that that really cause the system to be distressed, since we're typically closer to things like negative pressures and vapor pressures in many systems than we are close to the structural limit in the systems. So I don't know how much you work with this beautiful expression called the acceleration head. The acceleration comes directly from Newton's second law. Newton's second law tells us that mass times acceleration, or mass times the rate of velocity change, gives us forces. In our case, we think of forces as really pressure related under most circumstances. And this water hammer expression, or the acceleration expression, really just gives us the acceleration measured in G's. That is, dv dt divided by g is the g force, or the g acceleration associated with a particular event, multiplied or levered arm with this length of the pipe. And of course, we often work not in velocity units, but in discharge units, so the equivalent expression is shown with you there as well. And water hammer is that communication that takes place through this use of the acceleration head. This next image that I have is a really straightforward one, but a very helpful one. Lengths of the system are scaled in different ways, and we can imagine lengths scaled from as small as even less than a 10-meter length, but that's in our water conveyance systems a typical small length that we might be concerned with, to a order of magnitude analysis, 100 meters, a kilometer, or 10 kilometers. And the time rate of change of initiating our actions can vary over orders of magnitude as well. And the limit I put here is 100 seconds. So it could even be longer than that, but that's now moving us into the actuations in minutes. If we go to 1,000, we're talking about orders of magnitude in hours. 10 seconds, 1 second, or something very fast is 0.1 seconds. And if you just directly plug those values with a crudely estimated velocity of around 1 meter per second, very standard velocity in many of our systems under close to design conditions. Again, order of magnitude, it's not likely to be 10 meters per second. It's not likely to be 0.1 meters per second. So order of magnitude analysis, 1 meter per second is a pretty good value. And just plugging in that formula, you end up with these minuscule acceleration heads with long times and short lengths, to the ones that Mohammed already mentioned, extravagant values of acceleration head associated with long distances and short times. And again, water hammer needs to be used for those values. But let me just emphasize here that, again, the goal is to avoid accidents. And so from a design perspective, what we really want to do is to move the time step from, in this diagram, from the small time steps at the right to the long time steps to the left. Really, all of our water hammer protection measures are designed to extend the effective time over which change takes place. Whether we put in a surge tank, or whether we put in a relief valve, or use a bypass valve, or any other measure, we simply control the rate of speed, or we add a inertia value, what we're doing is we're changing the rate or the duration over which we invoke momentum changes. And the goal here is to move from that overestimate of an acceleration head where we need to use compressibility. Think of that as the crash, to move it to the benign values where we figure out how to accelerate or brake the vehicle without damage to the system and without damage to those that use it. So at this point, I'd like to introduce my good friend, co-author, and colleague, Brian Singh. Brian has been on the ground doing water hammer analysis for a great deal of time. And like most good engineers, I would say Brian is a reflective practitioner. He has run simulation programs on a variety of different models and platforms. And I think he's got some really worthwhile things to communicate to you, things that are really a long way from my current experience. I used to run lots of simulations, And just an aside that, in the past, when we used to run these simulations on personal computers and they were first coming in, they took many minutes or even hours to transact. Sometimes you'd have to go away overnight or at least go out for lunch and wait for the results. But I find there's a little bit of a tendency in modern analysts to sort of, get a working model and give up that, or a very complex model, which Brian will deal with. And what we're really going to encourage you is to take time not only to actuate change, but to take as much time as you can to reflect on what needs to be changed and how you need to do the simulation. The real danger is to rush, whether we're dealing with momentum changes or whether we're doing with the work of the analyst. Over to you, Brian.
Thank you, Brian. So, as Brian said, I'm going to, bring the perspective of consulting engineering, specifically from the water and wastewater industry. And I'm going to, speak about, in my experience, what I consider to be the essence of transient modeling. And so I've appropriately come up or grouped my ideas according to 3 S's. And they are, 1, slow it down, where we will appeal to the idea of mindful modeling. Number 2, simplify where and what you can, where I'm going to discuss, the both benefit and, disbenefit of model simplification and skeletonization. Also, I'm going to talk about sensitivity tests, because try as we might to get all the best inputs and validate all of our modeling variables, uncertainty is part of what we do, and how can we deal with that uncertainty? So first, we're going to start about slowing it down. Now, in my experience, it's not uncommon for hydraulic transients to be one of the last items considered in design. And usually this occurs at a time when the project's in danger of, if it's not already running behind schedule. So first and foremost, the practitioner should appeal to superiors and/or clients to ensure that they have appropriate time needed to complete the modeling task. And we can do this by emphasizing what's at stake from either under-designing or even over-designing our systems with respect to hydraulic transients. And regardless of the response we get, whether it's more time or not, we still need to take a breather. We need to slow it down and take time to think through the modeling task. Because if we just hit the ground running, well, we might be in danger of stumbling. So for example, a person could mindlessly just go through all the different permutations of system variables and run the hundreds of thousands of scenarios. But this would inevitably result in a waste of time, because what would end up happening is that what would be considered are eventually scenarios are inferior in terms of the surge pressure response. So if the modeler were to take time to be mindful and think through the problem, they could curate a short list of key scenarios. And these scenarios are the ones that involve the key operating conditions, which will likely give you the more conservative or representative transient pressure response, which can reduce the time needed to produce reliable and reportable results. Now, before even running a simulation, what we should do is take the time, slow it down to verify where possible and where within reason the model inputs as well as the scenario setups. So many of the commercially available software for transient modeling have built-in tools that can help speed up engineering validation of our models and can help it be very efficient to find things as orphan nodes, missed connections, as well as duplicate pipes in our systems and the like. Now, this step is one that should not be overlooked or avoided, right? Once again, we shouldn't just hit the ground running and just accept the model as it is. Taking the time to verify the inputs is important, because it doesn't matter how sophisticated our software is, it doesn't matter how powerful our computers are. The quality of our modeling outputs is directly related to the quality of our modeling inputs. And if we put trash into models, well, we are likely to get only trash out of them. Now, keeping along this idea of slowing it down, one thing is that, currently commercial available transient modeling software, they're increasingly sophisticated, and they have all sorts of tools that can help accelerate model setup. However, there is a word of caution that needs to be said when it comes to using some of these tools or features to speed up the model setup or initialization phase. And that's because, what might seem initially convenient in the model setup phase or model building phase might end up causing issues and inefficiencies down the road. Now, some of these issues may arise just from a misunderstanding or a lack of understanding of how a boundary condition might behave in a steady state and EPS engine versus how it behaves in the transient engine or during a transient simulation. For example, I once received a large network model, and it was an asset management model. But to help speed up the creation of this model, what the developer did was at every T-junction, instead of modeling the individual isolation valves or including the individual isolation valves, they tried to represent the multiple valves with a single valve at the confluence of the pipes. So right at that middle junction. Doing so reduced the number of valves they need to add to the model by 1/3 to about 1/4 of the number of valves. And it didn't hinder the running of the steady state model, because the steady state model, it simply considered that valve as a node element or a junction element. However, the transient engine was completely unable to be run, because in the transient engine, every valve element could only have one downstream pipe. And so literally this, the thousands of these valve elements that were in this steady state model had to be fixed in order to get the transient model to just run. So, here we see that what seemed as a convenience feature in, setting up the way the model was initially set up for steady state purpose actually led to inefficiency, right? And it actually led to increased time down the road to fix all these errors, all these mistakes, just to get the transient model up and running. And so we can see here, sometimes taking the longer path is actually the fastest path when we look at the totality of the modeling assignment. A lot of these commercially available software also have scenario management tools that make it quite convenient to set up adjacent scenarios or even sensitivity scenarios. Sensitivity we'll talk about later on in this presentation. But I've seen these oftentimes used and abused to the point where the inheritance of one model to one scenario to the next is not apparent. And you have yourself questioning what came first, the parent or the child, much like you might question what came first, the chicken or the egg. And oftentimes what I've seen too is that the wrong relationship is set up between scenarios. So where really a new parent line should be created, the parent-child relationship is what it's had or what is established. And this causes issues because then a change made to the parent scenario gets propagated down to the children's scenarios, even if it wasn't meant to do so. And this results in unintended errors in our model and scenarios, which then become more costly and cost more time and effort to fix later on down the road. So we can see here, being mindful when we build and set up our models can actually save time when it comes to totality of the modeling assignment. Now let's go to model simplification, simplifying what and where we can. Now, the increase of computing power has allowed transient simulations to be conducted on increasingly complex models. And oftentimes, actually more often than not, now I have clients who request that the transient simulation be conducted on their all-pipe model. And they're so proud of their models, as they should be, because lots of time and effort goes into building these asset management models, these all-pipe models, these digital twins. However, just because we have the computing power and the ability to run a transient simulation on a large network model doesn't mean we actually should. And the way I explain this to my clients is that a lot of times the network itself is the protection. And what I mean by that is the added dissipation and attenuation of the transient pressure waves can actually, that we see in these all-pipe models, can actually produce less than conservative results. They might be more representative. They're definitely not conservative. And when we model, what we want to, what we're often looking to do is come with conservative responses. We want to make sure that we're not under-designing our systems. And so what I tell my clients is the KISS principle, KISS spelled with a Y. Keep your simulations simple. Now, on the next slides, we will compare, the differences in transient pressure response of all pipe versus a trunk-only model. So we can see here, this is a relatively large pressure zone. It's so large, it's supplied by 4 pumping stations. We can see there along the southern boundary. And these pumping stations pump to 4 storage elements that we can see along the northern boundary. What's shown in blue are the larger diameter transmission mains. As well, we've shown here in yellow the smaller diameter distribution mains. And now we're going to consider the differences in the surge pressure response from a global power failure event across the zone for one pipeline segment, more or less central to the system, shown there outlined in pink. Now we're going to consider the surge pressure response in the HAL profile. And for those who are not familiar with these type of profiles, shown in green is the pipe invert elevation. We've also shown the vapor pressure elevation, so to help us identify where full vacuum conditions may be predicted in the model. The orange lines represent the modeling results for the all-pipe model, and the blue lines represent the modeling results for the trunk-only model. So if we look first at the orange lines, what we can see is that there's a starting HL around the 275 meter mark. And then we see that in the model, this global power failure event, there's a significant downsurge that propagates along the length of the line. Now, while this downsurge is significant, for more or less, the pressures remain positive along the pipeline. Once the downsurge reaches to the downstream storage element, it has a mild reflection as upsurge wave, causing the slightly higher than initial condition maximum transient HEL. When we look at the trunk-only model, however, we see a much more severe transient pressure response. What we see is minimum pressures predicted all the way down to vapor to full vacuum. And then we see a much more severe transient upsurge condition caused not just by the reflected upsurge wave, but also secondary transients caused by vapor cavity formation and predicted collapse. And so we can see here that the results are much more conservative for running this simplified skeletonized model. One can debate whether or not it's too conservative. But one thing we should know here is that that trunk model runs an order of magnitude faster than the all-pipe model. The all-pipe model in this case took hours on end to run. It was, even with all the computing power we have today, it's still something that you could need to run over lunch or even overnight. Whereas a trunk-only model can give you your results faster and they are more conservative, which might be what we're going for when it comes to design. Now, there are some pitfalls when it comes to model skeletonization that we should discuss. One is if the skeletonization process is maybe a little too thorough, that you can result in a change of flow distribution across the piping network, which in turn will change the resulting transient pressure response. Also, the removal of dead ends as part of a skeletonization process can actually lead to no longer conservative results because we're losing the local transient pressure wave amplification at dead end pipes. Also, sometimes relying on the automation tools in the large commercial software to merge pipes, to simplify piping networks. Sometimes these tools, even though they're sophisticated, they're not without the errors. And sometimes they might not move nodal demands, especially if those demands are contained in databases that are not part of the active scenario on which the skeletonization process is initiated. And so, the modeler has to have all these things take all these things into consideration. Once again, being mindful of the modeling process to know that these are potential pitfalls and not inadvertently create a transit model that's no longer representative or no longer conservative when it comes to design. Now, the skeletonization process is where we're trying to remove detail from the model, but there are times when we want to actually add detail to the model, and then we've called that digitization. Now, what are some of these cases where we would want to add detail to the model? So, for example, if we want to have a more representative pumping station layout, or if we want to add details for the vertical profile of a water main, a wastewater main, or other pipeline system. Now, the digitization process can be labor intensive, both in terms of just digging up as-built drawings, and then now digitizing and adding that information to our models. Oftentimes, what I find is the time it takes to digitize and update our models takes longer than the actual modeling process itself. And so how is it that we can speed up this process of digitization? Well, here I present to you, this real-world case on a project I just recently worked on, where there was a change in location of a downstream storage element, and it required some additional digitization of the model, which kind of added time, several weeks to the modeling task in trying to dig up as-built drawings for the section of the system where the new tank was going to be placed. And so I just take a look of what would happen if I compared the as-built profile shown in blue to an estimated pipeline profile, which was based on the model node elevations, which were representative of ground elevation. And if I just minus a standard depth of cover. And while you look at this, you can see in the orange line, the estimated pipeline profile. But yes, some of the absolute low points and high points are missed, but overall, the estimated pipeline, it shows good agreement with the actual digitized profile. And so what I'm presenting here and what I'm proposing is that as a first pass to help even the digitization process, that what we can do is with the models run sensitivity. You lower the model elevations by standard cover, you run a simulation, and you look where we may want to improve our understanding or our representation of the pipeline profile. For example, at locations where the model might predict negative pressure or vacuum or vapor cavity formation. And by doing this, we can reduce the amount of as-builts that we need to dig up, and we can reduce the amount of effort or the amount of line that we need to digitize, because we might find that for most of the system, using an estimated profile, which may not be 100% accurate, but it might be good enough for our modeling process. So that was the second S, that's simplify. We'll go now to the third S, sensitivity test. They said earlier, even though we want to verify all our inputs, we want to make sure that what we're putting into our models is good data. The reality is, we can't always wait all that time to find the perfect data, and sometimes it might be impossible to find that data. And so we have to deal with uncertainty, and we can do this effectively by using sensitivity tests. The results of these sensitivity tests can tell us where we need to sharpen the pencils, where we need to take a closer look at our modeling inputs. And I have two examples here, one of which is with wave speed initialization. Now we know the wave speed of a pipe or of a system depends on many different variables like fluid properties, flow properties, pipe material properties, and even geometric properties like the constraint on that pipe. And identifying the correct wave speed for every single pipe element in a large network model, it's just not practical. And so what you can do is assign wave speeds globally by pipe material and or pipe diameter. And then you can apply sensitivity tests. So for example, you're moving the wave speed up by 20%, down by 20%, and seeing how the differences in transient pressure response unfolds in the system. By doing this, we can identify the parts of the system that might be sensitive to our wave speed assumptions, and then focus our attentions, our digitization or our investigations into what might be the more appropriate wave speed assumptions for those parts of the systems that are sensitive to wave speed. Another example is pump and mass moment of inertia. This is one thing we always ask for on our projects, and it's probably the item that we receive the least, especially in case of existing old pumping stations where that data might just be lost. And instead of making a project sit on hold for weeks, if not months, and trying to dig up information that might not be around, what as a first step could be done is using accepted formulas, such as the equation, to first estimate what the moment of inertia is, running a sensitivity on it. If we find that the model is not sensitive, it's insensitive to the moment of inertia estimate, then maybe we don't need to hunt down that value. Maybe we can live with a conservative estimate. However, if we find that the model is sensitive to this value, then maybe we can justify the time and effort needed to hunt down these values. And once again, being mindful of what we're doing. Desensitivity tests can help justify either delaying a project to get better data or going ahead with less than perfect data. So there we've covered the 3 S's: slow it down, simplify where and what we can, and conducting sensitivity tests on uncertainty. And with that, I'll hand it back over to Brian to talk to us about the pitfalls of numerical modeling.
Excellent job again, Brian. That was very clear and very good. One of the things that Brian has already emphasized, of course, is that morass of complexity that we so easily and quickly enter into these days. Models are created for different purposes, and sometimes using one for the other means that we are, excuse me, we're caught with a model that is so cumbersome that it's not only hard to run, but it's hard to understand. And that preoccupation of being, the model told me that this was going to happen, and the model is based on assumptions and approximations. And too often these days we don't really verify what we have. One of the things that we've done a great deal of study on as a company associated with both Brian and with a larger group at Hydrotech that's mentioned in the bottom of our slides here is to verify whether pumps do what they're supposed to do. And often pumps deteriorate with time. They're no longer on their curves. And assuming that they are means all sorts of other internal adjustments to the models that are not relevant or not appropriate. And really the issue, again, is for controlling for calibration. One of the things I think is extremely useful is to try to start, as Brian sort of implied, with simple models and say, I'm pretty sure this matters. Add it in and say, what about this? And at some point you'll get a real good feeling for what the response of the system is in fact sensitive to and what it's insensitive to. The pitfalls for numerical modeling really deal with this chain of complexity as well, that we first were using computer simulations. They're quite simple pipelines with few devices, a valve here, a valve there, a relief valve, a surge tank, a single pump. But more and more we're pushing these systems for larger and larger systems with more and more complex pipes and more and complex components and devices. And as we do that, we're ending up with a greater and greater challenge of simulation modeling, with more and more challenge to get reasonable or calibrated results, but more and more information that can be obtained by direct modeling. In other words, by going out with sensors. And so as the complexity increases, typically there's more of the system that's built. And really the challenge there is this challenge between model complexity and calibration and risk and the analysis and effort, the budget that we have, the nature of the decisions that we're making. But it's possible that more and more of our changes are incremental. And certainly getting the key elements in first and gradually building complexity is often extraordinarily beneficial. I love this quote, and one of those ones that Einstein won, a very timely quote. Rutherford, who really worked with the structure of the atom, says, we don't have the money, so we have to think. And I think with respect to analysis, with respect to the decision space of what protection that we put in the light of the long life of many of our components, we really have to think, okay, what is essential? How can we evolve the system? How can we understand it better, not worse, as time goes by? And that's quickly or often that, access points and really listening to the system. I was listening to a Paul Simon, Art Garfunkel sort of reflection, and they said to harmonize well, they had to really listen to each other. And I think that goes very well for our long and our complex systems. And again, most of us here, I suspect, are not multi-billionaires. And so how many times in life have you really had too much money? A pretty rare event. For complex networks, just to reiterate a little bit what I've said, the analysis effort progressively increases with marginal gains in accuracy. again, thinking about the future, that we don't know what the system is going to be doing or what state it's going to be in or how landform and use is going to be changing over time. The model is less predictable. Calibration is more difficult with respect to it, and more expensive and often very frustrating. The really elusive components often have to do with, the presence or absence of error and the fact that error is much more mobile and yet not under as much control typically as the liquid portion of the line. And, design considerations often do represent those incremental changes. And so the value, availability, and economics of direct data acquisition has dramatically changed over my practicing life. I'm a graybeard now. I don't think the video is working very well, but more and more we can cheaply and easily monitor the system. Try not to be preoccupied with details, but to really look at that issue of modeling and getting data with enthusiasm and curiosity, and say, what on earth are you doing so that our actions can better harmonize with the system response and the decision that needs to be made. So a few comments in conclusion, and we're happy to take any questions that come up as well. But real systems experience of necessity a whole variety of different kinds of unsteadiness, from really high frequency noises that Mohammed is introducing and listening to turbulence and to regular noise in the system, to those controlled actions that are initiated from the boundary condition. And again, to really make the suitable selection depends upon what decision are we making and what device behavior is crucial to understanding that. And if we can control the devices, then the conveyance system usually looks after itself. It usually is something that is more automatic with respect to the response of the system. Again, one of the things that I think is just so useful with respect to this is to often think about compensating actions. If you're closing something, then seek ways of opening it. So you're shutting off flow to turbines, you're doing load rejection. So you seek ways of opening the system by making sure a surge tank is available or an air chamber or a relief valve. If you're opening the system up, that is, you've got a valve that you're opening, then you look typically for things that can compensate for that opening. An opening at the downstream end typically results in a lower pressure, so you look for things to maintain the pressure. And really, it's a matter of, if I can use the strange expression in this context, of learning to be a contrarian. In terms of design, it's a matter of compensating for what needs to happen for what can make it more gentle. And again, the key question there is, how do we cushion the system from rapid change? System response depends on numerous factors. Obviously, what the system was initially doing, what event took place, what are the location and presence of places where we can temporarily deflect the original effect to be reduced, to be mitigated, to be attenuated in terms of the system response. And certainly the system itself matters, but it matters mostly in our experience with respect to the way the boundary conditions respond to change. And again, one of the wild cards in that consideration is often the issue that Brian brought up with respect to digitizing the profile. It's the sensitivity of that profile to things like low pressure changes, where we want to avoid vapor pressure and negative pressures, particularly in potable water systems. And, again, the reminder that, I would just put for people that are more and more, I would say, seduced or more and more enticed by a virtual world, reality with respect to our models always gets the final word, but it's also the place where we have the payoffs of a good system design, a good system implementation, a good system measurement process, a good system set of actions and operations, are that the system works well. And oddly enough, that often means for our hydro stations and our water systems that they fly under the radar most of the time, that we are the health care professionals. We look after these systems in order that many people can ignore them, in order that they behave well, that they're under control. I commute often on buses and trains, and once in a while I'm on a bus with a rocket driver that they're just constantly braking hard and accelerating hard, and they're miserable to be in. And other times you're in a very gentle, very well-designed operator that knows how to take curves and brake and accelerate nicely, and you barely notice that you're on a ride at all. That's really what we want out of a transient analysis. We want a system that operates for long-term in a way that doesn't disrupt, disturb, or distress the systems that are using it or the people that are using it. Because really it's a human consideration. Anyway, we're delighted to be with you today. It looks like a really amazing overview of topics and overview of presenters. And this high level with some details we hope is helpful for you to frame and to conceptualize the nature of these hydraulic changes. We're happy to be here for a bit for some questions.
Thank you very much to Professor Carney and Brian. I can see here we have two questions. So I will start with the first one to Brian. It says,
Brian's.
for design, I'm sorry?
Or both Brian's.
Brian with the O, I think.
Okay. Go ahead, Brian.
Brian. Okay, so it says, for design, I understand that skeletonization helps, but when it comes to model validation / calibration through measured data, we have a hard time to have a good agreement, many unknowns, uncertain diameters, length, friction factors, valve status, etc. It feels like an ocean of uncertainties. So any advice on how to approach?
Well, I would say the model validation calibration shouldn't be done on the skeletonized model, right? You would validate your full model, whether that be asset management, all pipe model, right, with the best available data. And then the skeletonization is for the running of the transients, right? But I'm not sure if you noticed, but back in the slide where I showed the HL profile for the all pipe model versus Trunconi model, that there was a difference in the initial steady state conditions. In that specific case, that the starting HCl at the pump station was about 5 meters higher in the Trunconi model versus the all pipe model. And so when you skeletonize, you aren't going to have the exact same hydraulic conditions as your all pipe model, as your calibrated or validated model. And the question is, how much difference is important, right? And what you can do is run almost like that sensitivity test, right? If you have that validated, calibrated all pipe model, you can run your hydraulic transient on that and watch and observe the surge pressure response across the system. Then look at your skeletonized model, run it as well, the transient simulation, and look at the results. And and look for cases, am I being too, is the results too conservative? Or are they not conservative enough? Have I changed the flow distribution too much, right, to a point where it's now giving me results that are not representative? Now, when it comes to what is a good agreement, typically we look for something within 5%, 10% of flows and heads in the system. When we're looking at the all pipe version of the simulation versus the skeletonized, but in reality it's system specific, and it's something where you kind of have to do that sensitivity, be mindful and kind of run the two cases and look and apply engineering judgment and be like the results aren't going to be 100% the same. and that's not necessarily something bad, right? We are sacrificing a little bit of, maybe representative, or sacrificing a little bit of accuracy, but, what we're gaining maybe is a bit more conservatism and a lot better model runtimes.
Can I jump in for just a minute too? I think Brian's made some good points, but I think the level of agreement should always be passed between through the filter of what decision are we actually making? Are the differences that we're seeing going to lead to different actions, different designs, different choices? And if they are, they matter much more than if we say, okay, the pipe is strong enough. Our protection is working. It's working better than we assumed. That's good news. So I think to always go back to that issue of what difference do the differences make? And matter is what really matters in these situations. It's easy to be a perfectionist, especially if you live in a virtual world. The reality is the real world. I love that quote that Mohammed gave at the very beginning by Bascon. The real world is messy and chaotic and stressful, but it's also what we have to learn to cope with.
Thank you very much. There's another question, and for Brian Singh, and it says, what method is effective to verify model input and scenario setup? How if there are several model inputs and scenario setups? On skeletonization model slide, there is an in-zone storage that is not connected to the transmission main, but it directly connected to the distribution main. What factors cause this zone storage to not be connected to the transmission main?
So I have a question. Am I still sharing my screen?
Yes,
you are.
Yeah, so if everyone can see, I think the storage element being discussed there is the one furthest left in the north that is connected to a distribution pipe. But let me answer the questions in turn. What method is effective to verify model input and scenario setup? For me, typically when we're talking about a calibrated model, it's an existing system. And so we use existing model information. Typically, what we do is we ask for the client for SCADA data, flows and pressure histories, typically for maybe about a year for each of the key boundary conditions that we're going to be considering in our model setup. And we then use those to, help identify, is the model telling us, is what the model giving us correct? And, if, the flow distribution in the model is not matching what their SCADA and system data is telling us, sometimes we actually go out and recommend field data to get, sometimes better data. And we take a deep dive into the model. I can't tell you the number of times where I found, major connections that were not made in the model, right? Pipes that, that appear to be connected, but actually weren't. And that caused errors in the model. Wrong elevations, wrong pipe diameters, our network models, they're huge, they're massive, and they're going to be errors in them. As we try our best to have our models perfect, they're not perfect. And if we take a little bit of time, we'll be surprised of, leaky boundaries in our models, right? Of pipes that should have been closed that were open, pipes that should be open that were closed, right? Sometimes these are unintended consequences of sensitivity tests where we're a little bit careless and these things get propagated throughout our model. So the best way to effectively verify that I found in practice is by comparing the model results to actual field data, whether that be from dedicated field test or from SCADA, from regular operation from a client. Right, and then, some of the times the scenario that we want to model isn't something that we can safely, configure the system for. And in the case of proposed infrastructure, it might be something we can't possibly set up in a model. And that's where we have to, we're kind of hoping and relying that if the model is representative for the scenarios that we can, effectively both configure in a model and observe in the real system, if they are within reason, then we have to kind of almost take it on faith that for these scenarios that we can't actually configure and operate in the real world yet, that they will be representative, right? And sometimes we just have to live with that uncertainty, and some of the times we have to then be conservative, right? What is the maximum flow that we can get? Maybe we model as smooth a pipe as possible to minimize friction. Maybe that's when we look at more closely that skeletonized model. If we can't set up a corresponding real life scenario and get real life data in terms of flows and pressures, then we lean into the conservatism because we don't want to under design our system. And so, yes, there is that storage element there that's looked to be connected to a distribution pipe. And so this is one of those cases where I'm not showing the diameter. And even though that is, that the pipe there is classified as distribution, it's a large diameter distribution pipe. It's not a standard just 150 millimeter or 6-inch pipe or even 300. It's a much larger pipe. And in this case, the classification of it being distribution as opposed to transmission is just to deal with ownership. It was actually, in this case, it's a multi-level jurisdiction, and the pipe leading to that storage tank was actually owned by a lower tier municipality. And so, it's just, semantics. It's called a distribution pipe, but I guess it's probably more accurate to, call it a transmission pipe in that case. So sorry for the confusion that might arise from the plotting there. I could have done a better job, maybe even put that as a separate color for the larger diameter, distribution pipes.
Okay, no, thank you very much, Brian. Anything else to add, Professor Carney?
Thank you very much for this opportunity. I look forward to a great week. We've already started well.
Well, there is some time, and I would like to make a question myself, taking advantage of you both being involved in the practice of the profession. So it's maybe it's not exactly about what you just presented, but in general, I would like to know in hydraulic transient analysis involving column separation and rejoin for new systems, when your results end up requiring certain mitigation measures or ASME class for piping and instruments beyond the client's expectation, so that happens sometimes. Have you experienced pushback from the client, and how you have managed that situations?
You want me to jump in first, Brian?
If you would like to, sure, and I could tidy up.
I think one of the things that's so easy to do is to underestimate how bad things can be if things go wrong. Excuse me. One of my my PhD supervisor was a guy named Eugene Roos. He was quite active in Canada and was involved in many systems. And he was involved in analysis of a major water supply line for a pulp and paper mill. And he told them that it was underprotected. And he insisted that they should do more work. And they were very reluctant to spend extra money on the system. So eventually he wrote them a disclaimer and said, you guys are at risk. You need to know that. And several years later, there was an accident on that line. And they came back. And at that point, when they came back and realized the consequences of things going wrong, he couldn't talk about them spending more money than was necessary. In other words, the adequate protection was at a certain level, and they insisted on even greater protection than, in fact, the analysis or a prudent engineer would require. And I've held on to that story for more than 40 years, partly to deal with exactly the situation that you asked about. That you imagine that everything goes well, but in fact, there's lots of times that it doesn't. And I would just emphasize to clients, I would emphasize to the people paying the bills sometimes. If you think the risk is real, you need to communicate that as clearly as you can. And then if all else fails, get a disclaimer saying, I'm no longer responsible. You've superseded what needs to be done. You've accepted the consequences of this, and get them to sign off it. And it's usually enough to scare people into more prudent behavior.
So to add on what Ryan said is, yes, over the years, we've tried to take in the role when it comes to pipe class selection and recommendation of a search pressure class is to be almost like a trusted advisor. We kind of lay out the options and we communicate to them the risk. So we don't give just one recommendation. This is the pipe class. We actually say, if you want to design for the worst case transient condition without protection, this is what the pressure would be. If you want to look at with protection, this is what it would be. Right? And communicate to them, this is the level of risk that would arises from choosing to design pipe class based on with protection versus without protection. Now, specifically, your question was regards to kind of the secondary transients from vapor cavity formation and collapse. And in those cases where those do show up in our model, we actually do the third case. And we show with and without vapor cavities in modeling simulations. So we show them. If we allow vapor cavities to form and collapse and cause all sorts of secondary upsurges, this is what your maximum pressure could be. But if we suppress vapor cavity formation and collapse in model, this is what it might be. And we actually have a blurb that we include in those cases discussing the difference between discrete and distributed vapor cavity formation. We communicate to the clients that, typically our, commercially available software tends to be conservative. And, we agree with the conservative approach of, a discrete, cavitation in our models. But we also, say that sometimes that the maximums you get in the real system, they may not be as severe as this, but if you want to take the risk, this is what, it would be. And so we present to them, several different options, right? And so instead of kind of making the decision for them, we kind of help talk them through what the risks are and let them kind of make that final decision. But as Ryan says, we're kind of clear to, say that we think you should design for the worst case condition, which typically is without surge protection. And if you want to do something a lower level, this is what it would be, but you're taking on that risk.
Very well said. Thank you very much. And if you allow me, just one more question. Have you experienced it in these situations when you have pushback from clients? Have you experienced it that the client goes and asks to someone else to do a independent review or a different, the same model in a different software? Have you experienced that, and how you have managed?
We from time to time, some clients, especially for the more the more important or critical infrastructure, they would within the right ask for a secondary review. So it's not just, so I personally haven't actually had a client look at the modeling results then ask for the review. Normally they kind of at the beginning they already you kind of already have an idea that the secondary review will occur. So we're kind of fortunate in that respect. And I want to say is Brian, coming from that that background in research, he's kind of like guided us and mentored us to kind of be open and transparent with what and how we model. In fact, if anything, we give our clients more details than they actually want. And we invite, we usually in our reports put enough information that if anybody were to want to replicate our analysis, that they could without having to come back to us. And so we kind of put it out there for the client, and like, we invite a secondary review where, we're competent and, confident in what we did. But, if we did make a mistake, we're also humble enough to, want it to be caught, right? So we invite secondary reviews, but we've never been in a situation where we've given the client an answer that they didn't like so much that they kind of went looking for another answer elsewhere. In fact, more often than not, one of the very first projects I worked on was we were asked to be that secondary review of another consultant's work, because maybe they weren't as transparent with what they were doing and how they were modeling, and the utility, water utility in that case, they wanted us to come in and kind of review what was done and make sure that nothing was missed. So knock wood, we're fortunate that we haven't been on like the negative side of that, right? And we hope that we'll continue to do good enough work that our clients would kind of not just take us at our word, but they'll have enough what they need to kind of do an independent review if they need themselves.
And perhaps I'll just add another thing to it, since again we have a little bit of the luxury of time at this point. But when I first started doing this transient analysis, particularly of complex systems, that was part of my PhD work in 1980s. So it's 40 years ago now. There was a huge sense in the practical field that there were no transients in distribution systems, that they were automatically suppressed by the nature, the topology, and the wave interactions, that they didn't matter. And one of the huge revolutions that's taken place in my time has been the improvements that have taken place in sensor and measurement technology. And as we put more sensitive transient transducers into complex systems, we've realized how wrong we were, how many significant waves and wave interactions are in those systems. And yet there is also that still that overwhelming complexity of real systems. But the world has changed. We're much more alert to what can go wrong and how it can go wrong. So I think in most cases we shouldn't be prima donnas. We should welcome the possibility of someone else looking over our shoulder. I'd much rather any errors that we might make or any oversights that we might take place in our analysis to be caught before they're implemented. That it's a good news if people want to check them and want to have a analysis of what takes place, because these systems are crucial. They perform vital operations, and when they fail, the consequences can be huge, not only to the to the utility or the owner of the system, but also to the people that are adjacent to it or use it or inconvenienced by it. So on those rare cases where a secondary opinion is required, I think that opens the door for discussion. One of the things that happened in the airline industry was the idea that you can challenge the pilot. And when the pilot could be challenged, you had that cockpit sort of query environment where those challenges were to be accepted, and happened in the medical field as well. Accidents were reduced. That we cannot face these as unquestionable prima donnas. And as Brian said, one of the things we've really tried to do in short course and other things is to give our potential clients or our actual clients a feeling for why these matter, what the consequences can be, how things can go wrong, because the more they know, the more they're likely to value our services. I worked with an engineer who was quite famous a number of years ago, and he always wanted to keep the details in a black box. So you have to trust me. I think the trust should be because we understand each other as much as possible, and not because we don't. That was a longer answer than you might have wanted, but thank you for the great question, Jose.
Thank you very much for the very interesting insights. I'm sure we will be able to continue talking about this, especially on Friday on the roundtable session. I understand your point of view, but I have my own. I know that other panelists have had troubles with these secondary reviews because of using different software. So that I think it would be interesting for the attendants to listen and learn from that. So many
Agreed.
thanks to both presenters in this session.
And my apologies for the issues I've had with background and the fact we're a little bit short, but get up and stretch. They're useful to exercise. That's a valuable transient. Sorry, I didn't mean to interrupt.
Well, next session is scheduled to start in 22 minutes. So I don't see more questions. So we'll take these 22 minutes.
Sorry to cut you off. I think there might be one more.
Really? Oops, sorry for that. Oh, okay. Yeah, one more came in. I will read it, and it says water utilities and companies that manage the systems are often risk adverse and prefer not to test their systems to water harm events. How can we communicate the importance of data in model validation? There are always uncertainties in our models, and especially in old systems. We might not get the full story.
This is really a good question. I like it and very timely because it's actually a situation that we were going through quite recently, where there was the, I guess, engineering design team of a water utility really wanted transient tests to be done on their system, and they were all for it. Because they were having operational challenges, and they wanted to truly understand how their system was operated and the risk to it. The operations side was completely against it and was shutting it down. They didn't want any transient tests to be conducted on the system, and we were kind of caught in the middle. One department asking us, begging us to come out and do these field tests, and the other one refusing to allow any tests to be done. And what we were able to do is do a compromise. And what we did was we used transient modeling to kind of show what a safe scenario would be. So in this case, instead of a power failure event at firm capacity, we looked at, well, what, and this was a pumping station with a 3+1 configuration. So 3 duty pumps, 1 standby pump. The engineering department wanted to see the firm capacity power failure. We were able to show what the firm capacity, the 2 pump failure, and a 1 pump failure would look like. And in this case, these were VFD pumps. And with modeling, we showed what a controlled normal shutdown of a single pump would be. So going from 3 to 2, right? 2 to 1, those being emergency stops, and then the final stop going from 1 to 0 being a controlled stop of the system. And when we were able to show what we consider to be mild pressures, we were able to get a tentative field plan in place where operations were on board with just a step test and with live data. And so when we did the 3 to 2 test, we looked at the data and we compared it to what the model said. And they were able to look at that and say, okay, yeah, you know what, the real system data is close to what your model told you. It's within safe ranges. And then they were able to greenlight the second test, going from 2 pumps to 1. We stopped, looked at the data again. And once operations were, once they felt confident that the results were good, then that final test, you could do a controlled shutdown, right? This isn't what the engineering department originally wanted, right? They wanted to see what the firm capacity and see what the risks were, and operations didn't want that. And finding that compromise where we were still able to get field data and still use it to kind of calibrate the transient response of a model. And so what it was empowering those who were against the work, letting them, look, you have full control. You can greenlight the next additional tests. We will do it stepwise, but showing them what some of the results may look like, right? So using the data from a uncalibrated with respect to transient model, right, and doing a stepwise process, you may be able to get their buy-in. That being said, there've been cases where absolutely the headwinds against that work is so strong, you will not be able to get it done. I remember flying all the way to Mexico, being asked by clients in Mexico to do some pump tests, and this was actually during swine flu. And the populace actually staged protests in front of the utilities headquarters, preventing us from leaving to go do the tests because they did not want any change to be done in the water system, because they were afraid of contamination, of intrusion of untreated water and contaminated groundwater into the system, which would further exacerbate the health condition that was going on at that time. Having put together a fuel plan, having it approved beforehand, planning this trip, going all the way to the city, traveling to another country to do this test, and having to literally spend the day, trapped indoors because of a protest and not being able to do the work. Sometimes all the planning in the world, all the results beforehand that you could show them isn't going to change people's mind. And sometimes you just have to accept the fact that you're not going to be able to do the field tests that you want, and you have to live with the uncertainty. And then you end up doing more sensitivity tests than you would otherwise want to run, but they're not necessary because you don't have field data to kind of back up your model setup and calibration. So sometimes you'll be able to get people on board, sometimes you won't. And to help get them on board, you can show them with results of your modeling with your uncalibrated model.
Thank you very much. Very, very real experience there. I have suffered similar things. So I think we are done with this session. Next one will be run by Jose Vasconcelos in 15 minutes. So for now, let's take a break, and we'll be back in 15 minutes. Thank you very much.
Thank you all.
Thank you.
All right. I think it's, well, depending on your time zone here, we are in the US Central Time. And on my clock is 9:40 a.m. And we have here, like you have said, just an incredible lineup of speakers and presenters. And we are going to continue our course today, and it's my really distinct pleasure to introduce Professor Chaudhry. Professor Chaudhry here is, I think, is our last presenter for today, and he is extremely accomplished hydraulic researcher, professor. He has his undergraduate in University of Engineering Technology in Lahore, but both of his master's and PhD was also at the University of British Columbia. After serving as a professor at Washington State and Old Dominion University for many years, Professor Chaudhry has been at the University of South Carolina and has taken a number of roles at that university that includes being the associate dean there in the College of Engineering. Dr. Chaudhry has received a number of recognitions in his career in terms of both IAHR, but ASCE being a distinguished member there. He has received the Hunter Rouse Award, the Hydraulic Structures Award, and has had a number of partnerships, recognitions. I personally know Dr. Chaudhry, but before meeting him in person, I knew him about the books that he had, and I think many of us also have the same type of interaction with him. So again, it's really my great pleasure to introduce him to our training series, our seminar series. We really appreciate Dr. Chaudhry for joining us. Do you have your slides ready? Would you like to present them?
Sure. Okay, can you see?
Yes. I think you can start your presentation.
Yeah. Okay, let me change it to, oop. Well, thank you very much, Jose, for nice introduction. What I'm going to do is I'm going to be covering a little general presentation on modeling software for hydraulic transient analysis. Since there are lots of academic people attending rather than just covering one model. And here is a brief outline. So we will have brief introduction to hydraulic transients, which I'm sure we have had excellent presentation this morning, starting with Mohammed, very elegant theoretical approach. And then, of course, Anton and two Brian's giving a practical approach. So what I'm going to do is I have been wearing several hats in my career, starting from as a graduate student. There's this model we are going to discuss, we started. Then worked as a practicing engineer, mainly on hydroelectric power plants, joined the academic world, and as well as involved with some consulting, actually in all 6 continents. And on another topic which came up during the previous presentation, have been involved on some litigation issues where lawyers get involved. And at the end, if there is some time, I will briefly touch on that. So let's start with this a brief introduction on hydraulic transients, and then I will discuss briefly on this code, how it was verified, applied, a number of challenges. So it is not just running some models, but give you some insight into what is involved. Okay, what is transient flow? It's intermediate stage flow between two steady states. So this definition is quite similar to what we have in ordinary day-to-day life, where we say steady boyfriend, steady girlfriend. So that is how this steady flow means. Things are not changing at a location with respect to time. While in pipe flow or in open channel flow, transient means almost universally not just unsteady flow, but non-uniform flow. That means your flow variables are changing with respect to time at a location, as well as with respect to distance or space at a time. So in mathematical terms, you will have partial derivatives with respect to x and partial derivative with respect to time. Typically, cause of transients are opening, closing valve, as we have been discussing this morning, starting, stopping the pumps, starting up a hydraulic turbine, accepting or rejecting load, which means mainly opening the wicket gates or turbine gates. While this used to be normally a very specialized field, used many, if you see the earlier papers, main method of analysis used to be graphical methods, then came numerical, and of course, once the computers became available, it became a kind of different issue. So here it reminds me of, because of this complexity of the subject matter, this particular cartoon where person is saying, I thought you were throwing snowballs. No, I was not throwing snowballs. Sometimes I don't understand you. And then the person says, well, sometimes I don't understand myself. So that is roughly, having worked in the field long enough, I would feel still there are several areas where we are learning, understanding, and proceeding further. So computer codes. Well, if you have the knowledge and time, typically best way to proceed is you develop your own. If you have the money, you buy it. And unfortunately, nowadays, or it has been for some times, rather than developing or buying, people borrow. And in that case, you might have the code, but you may not have the backup documentation. And as a result, you may or may not know what the program can do. And equally important is a particular code cannot do. I think maybe not in other countries, but in the United States, that part, if misused, it ends up with litigation, lawyers get involved, and unfortunately, it becomes a very costly proposition. So I'm going to show some here. using models as a box can be very dangerous. Why? Because you have to know the model, what governing equations it is based on, whether it has appropriate boundary conditions, does it uses proper computational procedures, and what are the limitations of those. And of course, once you have all these three areas covered, still you have unknown of uncertainty in the parameters. You will be utilizing system dimensions as well as various approximations or assumption concerning the operations, what is being done and how. So that must be understood. Just taking a code, either buying or borrowing or developing, it is equally important that the person utilizing the model is aware of what the model can do, but at the same time, equally important where a model cannot do, because that can result in rather serious consequences. Question in previous discussions was raised on what do you do? Well, easiest way to show somebody who questions something or raises some questions, best is to show them what might happen if the system is not designed or operated as it should be, because if it is not, results can be disastrous. Unlike geotechnical, where your errors are most of the time buried, in hydraulics and fluid mechanics, unfortunately, any mistakes you do, if it ends in a disaster, whole world knows about it. So I'm going to show you some photographs of different projects, almost at all continents. So I'm going to start with this nice one from Japan, Oigawa Hydroelectric Power Plant. Due to equipment malfunction and then unfortunately some operating errors, turbine inlet valve was slammed shut. It generated fairly high pressures. And as you can see over here, this penstock, which is almost about 1 1 inch thick steel, just opened up, just like we used to use scissors to cut during our, how would you say, elementary school days. Well, once this penstock failed here, so you have uncontrolled flow coming out. This is at this particular location. So what will happen? So flow will increase considerably. And as a result, you have negative pressures and you have a penstock collapse. This one is from United States, Big Creek number 3 hydro power plant. And here, this is turbine inlet valve. And if these ribs were not there, this will have similar situation, but still it resulted in a kind of major disaster. And how about Europe? This is from Switzerland. This particular penstock collapsed because during draining, unfortunately, the upstream air went, water was frozen. So as a result, air couldn't get in. This one again from Europe, a design problem, column separation, and part of the casing in the pump is gone. Well, South America. This is a power plant in Peru. Penstock used to have this strait, except due to transients in the power plant, you have this disaster here. It looks like people in Africa don't do mistakes, so at least I don't have any project to show, so all kudos to them. All right, let's briefly discuss on model development. So what is needed? Well, first items you need is the governing equations, and I'm showing these two sets of equations. Reason for that is that first set, which is continuity equations, which is conservation of mass. In civil engineering, we call it continuity equation, and momentum equation. They have all the terms. Convective acceleration, well, normally in typical transient conditions, these terms are small. So if you neglect and convert flow velocity to rate of discharge Q and pressure rather than in PSI, pounds per square inch, you convert it to piezometric head, which as civil engineers, we typically use H. So these equations become simplified and in this form. Reason for our showing these is not only that we are what equations you are using, but really what I want to point out is that depending on the code you are using, please make sure that your original governing equations on which the code is based is using consistent boundary conditions, because many times that is not the case. Because if you don't have consistent boundary conditions, you will start generating disturbances at each computational node. So here, like if you're using simplified equations, you have conservation of mass or continuity equation. That is, you do not have your flow at one location is flow equal to second location plus any lateral inflow or outflow. And second one, you can use simple Darcy-Weisbach or any other exponential formula for computing steady state hydraulic grade line. Well, in case your equations are these, where your modeler said, I'm going to keep all the terms, then it's very important, like the first one, conservation equation, this will be your equation you will use to compute the initial steady state. And here you will neglect partial V, partial T term, and this part is the one which you should use to compute initial steady state. If it is not done, your initial steady state is inconsistent with your original governing equations, which may make a small difference, but other cases, many times when you're including G sine theta terms, it may be making significant difference. So please keep that in mind. All right. These governing equations are non-linear, hyperbolic, partial differential equations. Question you might ask, why we have to worry about that? Well, if you want to, since there are non-linear terms, we do not have closed form solution. So as a result, we have to use numerical methods. So here are a number of different methods which are available. mostly method of characteristics is the one which is being universally utilized for transient, most of the transient flow models, except there is one like developed by Corps of Engineers, which uses implicit finite difference method. Finite element method started maybe 20 years ago, rather applied 20 or 30 years ago, didn't get much use. Spectral methods, okay for periodic flows, but not for normal transient conditions. And boundary integral methods, same way, not as suitable. So we are going to be covering in this presentation mainly method of characteristics. The model I am presenting utilizes this method. So here it is that we have method of characteristics. We will solve these two partial differential equations using this method. And what does this method do? Well, it converts our partial differential equations to ordinary differential equations. And if you remain along those lines in the xt plane, you are not making any approximation except when you start writing or replacing the friction term. So utilizing these equations, this is the model I mentioned I will be covering. So this is, I'm calling it water hammer, WH, transient flow model and all that line. Okay, this started with my MS thesis. And since then, it has been going through continuous, I would say, modification, upgrades, depending on where it was being applied or what others who were using what they needed. And as practicing engineer, consultant, and then of course, as a researcher, once you join the academic worlds. In this, we have turbo boundaries, almost all boundaries we can imagine, turbo machines, control devices, other apprentices, and these are simulated. And if you want to see what is the basis of these computational procedures as well as boundaries, most of it is, I will say, more or less presented in my book, which is third edition now, and most of the papers. So all the information is there, so you can decide whether particular application you are using is suitable in this or not. While this being in English for our Chinese friends, it has been translated, or actually it was translated right away, third edition in a matter of less than a year, although first edition, it took some time, the translation. So if somebody is interested in Chinese, it is available. Okay, so originally it was developed in Fortran, and last couple 3 years, we converted it into Python, and presently it is also available via cloud computing. Okay, what is, I think it's user-friendly. So your input, to put the input, we have a WH input separate software where interactively you can input the data, and as you are inputting the data, you have access to the, what should I say, user's manual. So you can put in the information interactively as well as manually if you want to. Okay, so what is needed? You need first the general information, how large your system is. And very important here, how is going to be your output? So output you can decide what are the various variables you want to store for post-processing. So there are all kinds of options available. I will not go through any of those details, but those we can provide. Steady state conditions. You can have the program computed, or you can run the model using the specified initial conditions sufficient time to converge to the steady state. So that option, both options are available. For each conduit, of course, you put in the data. And then these are the nodes, as I mentioned, almost all upstream, downstream, series, junction, branching, etc. Important one I would say would be Francis, our propeller turbine with PRV, pump turbine, and of course we have all this cooling water condenser, and you can see specified boundaries. So utilizing these, you can more or less analyze any system you want, and this non-reflecting boundary, if you are considering a large system, if you want to, you can put this boundary there and utilize the model. Okay, so there are 3 different types of governors, PID, Woodward, and again, ISIA is in there too. We can include any other. It's very easy, simply writing a short subroutine, maybe 5-10 lines to specify, and then that can be run. Machine characteristics, that is the item which is very hard to get. Typically, if you have really old systems you are analyzing. So for convenience purposes, in the program itself, we have characteristics in all 4 zones on 16 pumps and 11 turbines covering the full range, as well as over a wide range of specific speeds. So online version is in Python. Okay, well, for application in water distribution systems, we have combined it with EPA net, and we are calling it Trans EPA net. Reason being that in the US, that model is used quite extensively. So most of the time, data input is a long time sink for doing these models. So here we can use the data you might have generated in EPA net, and then supplying the remaining information, model can be run to do the transient calculations. Okay, one very important item, as I mentioned, that you develop the model, but you must verify it against lab results, field results, if possible. Utilizing a model without some verification can be troubling. Okay, here is some comparison. I'm showing just 3 over here, but it has been verified against several other field applications, as well as in the labs, which we have been doing over the years. So here is this generating station, rather large one, in Canada. So it is producing, how would you say, following load rejection. You can see the pressure rise. Peak is pretty good. Same way if you utilizing the governor, or you compute your wicket gate opening versus time comparison between the measured, which is full line, and computed is the dotted line. Comparison is pretty good, except oscillations, how should I say, with time in pressure, in real world, they die down rather quickly as compared to computed ones. We will discuss that in a minute. And same way, if you see the peak overspeed for the turbine is predicted pretty good. The second one is rather high head plant, close to 1,100 feet. You can see 336 meters elevation here, a long unlined part line tunnel, penstock, and in this case, there is a pressure regulating valve, no surge tank in spite of this long line here. And if you compare, again, you can see pressure oscillation computed and measured. Compare reasonably, or rather quite well, except if you are looking for time variation, computations show the dissipation is not as much as is the case in the actual project. Okay, these were the two power plants. Well, here is wind gap pumping plant, really large pumps. And here, if you compare, again, full line is your measured and dotted are your computed values. And this is the pressure comparison, downsurge following power failure, and closing the discharge valve in 22 seconds. I have a similar comparison for where this valve is not closed. Difference is really not. It produces or predicts these values reasonably well. Well, having done this and few others, you start feeling very comfortable. Model is predicting things as it should. Well, not necessarily. Well, here is an application where during commissioning of the power plant, rather large, 550 megawatts, at 257 load, 257 load rejection, there is this pressure spike here and maximum pressure almost reaching the design limit of the penstock. So if you see over here, this is the pressure spike in the penstock. And if you really see time-wise, pressure spike is starting or it's little before what is happening in the penstock itself. So this particular case then gives you a kind of that be a little cautious. Don't start assuming whatever your model is producing is really, you can use, it is universally accepted or it is correct. No, there can be limitations, there can be possibilities. So be on the lookout. Okay, here is then following this, I checked around. So there are in Francis turbines, if you have a low rejection, this is typical most of the time. Well, this is abnormal one, a little abnormal. But this is one which is really abnormal. You can see this pressure spike. So a question might arise, why? What do you do? Well, in this case, I don't think we have any particular yardstick or any criteria one can use other than that look for what is the length of your draft tube as well as how you're having your load rejection. So here we are simulating one-dimensional flow in the draft tube. Well, you can see here when it becomes part gate, your flow is really not one-dimensional. So assuming that your results would be accurate and precise is really asking for too much. This is the second one. This is from Papua New Guinea, Okmenga power plant. I was consultant on this because what happened, well, actually during design modifications, and then afterwards when both draft tube gates were blown out. Most of the load, almost all the load is from mining operations. So your shovels or electric shovels come on and off periodically. So question was, and in this case, after this accident, powerhouse was flooded and owner didn't want that thing happening again. So as a result, we wanted to analyze why it happened so that it doesn't happen again. Tried all different possibilities. You can simulate failure of one draft tube gates on one unit, but having failure on the second unit at the same time almost just could not reproduce that. So this is where forensic engineering comes in. Not necessarily if your model has been producing good results, you can predict what happened, because in this case, I thought maybe it's a resonance problem. So try to have different periodic off and on, even multiple off and on. Well, still you could fail the gate on one, but not on the second one. Well, so we still have to find out, okay, let's see. Normally when you have a failure, you look for exactly at that time what was going on at the project. Was somebody opening the gates, closing the gates, doing something? Well, in this case, that data was there, but still it was not leading to any particular conclusion. Well, let's look back a little backwards. Well, what had happened was just in few days or a week or so, they had done some maintenance work on one of the units, and this is after looking all through there what was done. It became apparent that on one of that unit which was maintenance work was done, the gates were not torqued to the proper value. So as a result, as soon as there was small disturbance on load, those gates, wicket gates on this slammed shut. It created negative pressures in the draft tube, and that when columns rejoined, very high pressure, so it failed the draft tube gates of that unit. On the upstream side, this sudden slamming of the gates produced very high pressures, which just went to the manifold and then went into the second unit and failed the second one. So at least that was our conclusion. So after that, we were a little assured, but since then, this was many years back, haven't heard, so most likely everything is working fine, because typically when things don't work, you hear back very soon. This is the one I'm working presently, case of, in US, we call it forced main. You might call it wastewater pumping. So this is sewer line for waste water. So what is happening is they get a sudden surge on when they trip the pumps. And here is a rough oscillation. So I'll try to see what might be the reason. Still working on it at this point, but just preliminary information. If you just assume that you have a power failure, there is a check valve and it closes as it should, your oscillation die down very nicely. While if you keep the check valve open till the flow reverses and develops a little bit, so with 1 meter per second, you can see this is the pressure rise you get. So again, in this case, when you are looking at various, or when you are investigating this kind of things, please look for various other possibilities, not just on the model itself. Okay. So lots of programs, codes are available at this time commercially. I'm sure all are doing very well, but still there are some challenges. So one is unsteady friction. Is like, as you might recall, this model I discussed, it is utilizing steady state friction formula, which is what Darcy-Weisbach in this case. But question arises, is really that important? Well, answer would be maybe. Most of the time, no. If you are just looking for the first pressure peak or first downsurge, it may not make that big a difference, but it becomes very important in case you are going to restart your pump or turbine. Then in that case, you want to make sure you are doing it at the proper time. Otherwise, you can make things worse. So what does this happen, or rather, what does this unsteady and steady friction, what difference does it make? So this is one of my former PhD student. He did this experimental test, and his thesis was actually on unsteady friction. And he developed a 2D model. So here I'm going to show some comparison. So here it is for one-dimensional model. You can see experimental is this dotted line. You can see how, sorry, yeah, that's right. Here is the other way around. So experimental is the dotted, so it's dying down nicely. But when you compute it, you can see it's going on forever. This is at the well, at quarter point. That is right over here at this point, all 4 locations. Comparison peak is fine, first peak at each location, but not as you progress with time. Well, as I mentioned, he developed this computational, or rather quasi 2-dimensional model, and there are a couple of other procedures, methods available. I will just convolution integral, I will discuss that in a second. Now, these 3 methods, and then instantaneous acceleration-based methods, those are more or less becoming more common, and we will discuss these in a second. First one gives very good results, as I will show you in a minute, but computationally very time requiring. CPU is large amounts, so not useful for, forget about practical applications, even for comparing in the lab. Simulation takes long time. This one typically not as useful except for laminar flows, and this third one is a nice contribution from Professor Bruno, and that is what we are going to discuss. So here is unsteady friction that is utilizing the 2D quasi model. You can see it's showing reasonably well, although I might add that still there is a phase shift. So although it's predicting the peaks okay, it's predicting the dissipation okay, it is not predicting the time evolution as nicely as is the case with the peak or dissipation. So what is done in this instantaneous acceleration-based methods? Well, you say, well, let's keep or divide this friction into 2 parts. One is steady state, which we are doing. Another is unsteady state. And to include that, you have 1 coefficient model, 2 coefficient model. So utilizing these, again, one of this former postdocs, we did this work where we got data, experimental lab data from 5 labs from all over globe. And we got, I believe, both upstream well closure as well as downstream. Downstream well closure data was more, or rather more tests data was available for those as compared to upstream. So in each case, we utilize both of these models, 1 coefficient and 2 coefficient. And to determine the coefficients, we utilize these genetic algorithms so that simulation is producing the same results as was measured. That is your pressure oscillation. You keep on modifying your K value or your coefficient value till it matches. Well, then we thought, well, let's plot and see if we can get some sense out of it. Well, unfortunately, we were not that successful. You can see these points are all over. So although theoretically we can say that these models are good, but if you want to apply it in real world, picking up these values might be challenging. Another paper recently came, and I thought it was really a good contribution from Italy, Professor Pazanga. And there he showed that maybe gas release during pressure oscillation might be affecting damping oscillations. And as you know, this is this plot from Kabori, 1955. On this side is your air content, and on this side is velocity of pressure wave. And you can see just having a very small amount can reduce your wave speed to almost 50%. So in case you are reducing your pressures to low values, then question arises, what is the value of that wave speed? So if it is changing and you are just using the higher values, your results can be not that precise, 1. And second is, I don't think anytime you really know how much is the air content in the pipe or in the water you are simulating. So if that is the case, then computing your wave speed to nth decimal may not be all that essential. So, and this particular aspect, my recommendation have been that in method of characteristics, since we have to use interpolations, since you can't have same time step in all the pipes because of different wave speed, so you can adjust it slightly and you will not be too far off. That might be better or might give you better results as compared to, how should you say, utilizing the values as you entered, but interpolating. Okay, one other thing which I think needs some examination, and that is what happens to pressure wave as it propagates and reflects. In all the present models, at least what I'm aware of, they assume that your pressure wave moves, goes to the boundary, gets reflected, comes back to boundary, gets reflected, and each reflection, it is 100%. Some models might include the loss over here in terms of energy loss, utilizing just like intake losses, while this reflection is not same as what you have personally in the real case. So here is pressure wave dissipation. If you have at series junction, again, we have all these equations developed going back many years. And this is the test we did. Going to show you here. Here is the pipe coming in, and we put in lots of these particles, and you will see the wave comes. Maybe let me go back to here. Here. Okay, so we just put, so wave is going to come. So you can see it's expanding in the tank. So assuming that it is 100% reflection here may not be the case. So here you will see now this wave has, on the left side is the actual pipeline where we are closing the valve. And so here waves are coming back and forth. So you can see each time it's coming, it's not as strong as was the case beforehand. Okay. All right. While in acoustics, they have reflection coefficients very nicely computed in terms of Mach numbers. So here is reflection coefficient for upstream reservoir. Here is reflection coefficient for a dead end. And similarly, I think here, depending on if you are assuming it as a rigid wall or acoustically soft wall, different values, you have to compute the impedance and you can have the reflection coefficient. Well, what if we do that? Well, here is frictionless system, and we include reflection coefficient in our model. Well, in that case, you can see this is dying down reasonably well if you're including different values of reflection coefficient. So here is again different simulations. Upstream boundary, you include or rather handle it in terms of reflection and include the entrance losses. That's here you can see different R values without reflection. And you can see it's just going on and on forever. R is equal to 1, 0.95, 0.9, and so on. And this right side is where entrance losses are not included. Okay, so two other codes I wanted to briefly discuss, system of surge tanks and then the channel. Well, this previous discussion we have had so far is based on what is called distributed system approach. So that is where you have steady state, where you have pressure waves moving back and forth. As Mohammed this morning showed very nicely utilizing equations, what are the limits or what are the range of parameters you should look at where you should be utilizing one approach versus others. So typically in the past, that is going back almost 60, 70, 80 years, lumped system was, that is all you could use. So most of the models you had based on lumped approach, but this one is reasonably okay if you are analyzing stability of surge tank or a system of surge tank. So where we developed this particular code was this system, or rather two power plants in series in Ecuador. They had, I believe, if I recall correctly, total of 9 or 10 surge tanks. So analyzing that in a distributed system model, first is your data is large, and second is you can analyze the maximum and minimum levels, but analyzing the stability becomes questionable. So that is where, if you use a lumped system approach, you can utilize nicely these different models. It's a little easier because you can include your nonlinear terms, one, but at the same time, as you know, your system is unstable only if you have constant power case. If you consider constant gate, then your system is inherently stable. So if you combine it constant power case where you say you can open the gates only up to the maximum limit, and then it becomes constant gate opening case, then that system becomes kind of periodic oscillations, but it is not unstable. I had a paper long time back on that. The second model is combined free surface and pressurized flow. This is a kind of much more fun or challenge, because here not only you have transients in your closed conduit, but it can pressurize. And Jose has been doing great work in this area. This particular one, we are rather just have been developing this, and one other item was added, was calculation of air pressures. As your transient water surface level rises or drops, your air volume increases. You have air shafts along your sewer line, most of the time storm or storm sewer. And this particular one where this part was modified, or this code was modified, was for Vancouver, BC. They have a tunnel which more or less carries entire stormwater as well as their regular sewers. It's a combined sewer system to the treatment plant. And there are air shafts as this tunnel is going underneath the populated areas. And unfortunately, during summer, it used to get lots of kind of bad odors. So they will come and seal the shaft at the top, and soon became kind of questionable, would it be detrimental to the structural stability? Well, that's the time we developed this code and analyzed it, and luckily things have been okay. So this is the second one I want to discuss. Presently, we are kind of concentrating on this digital twin. This is not just the computer model, but digital twin, if you see the real definition, and that is what has been or is being utilized in electrical engineering, mechanical engineering, there they couple it with data from the actual operation of the project. So this particular application we are working on is we are utilizing AI-based optimization methods. Predictive modeling is done as typically is available, but we are combining this with input coming back from the actual system. And main emphasis at this time is to optimize chlorine input or a chlorine injection into the system. And that is where utilizing actual values in the real-time simulation is really helpful, because you can not only predict what your flow and pressures are in the system, but at the same time, you can get some actual field measurements from the actual project, compare it and adjust it. So it's a kind of nice challenge. I would say, but it is fairly enjoyable experience. Okay, summary. What is needed? Please, anytime you use a model, whether it is yours, developed by yourself, purchased from some commercial lender, purchase or lease from commercial lenders, and definitely if borrowed from somewhere, make sure that your model is covering all the assumptions which were made for the development of the governing equations. It utilizes the boundary conditions and appropriately. I have seen models, unfortunately, where steady state models being utilized to compute flood water levels in rivers and streams. Pretty common all over. That's not, shouldn't be the case in this day and age. Appropriate boundary conditions and data. And that is where uncertainty comes in. So that is this last item here. But even you might have appropriate boundary condition in the model, but if your data is not, which is, it should be, your results may not be or will not be as precise as they could be. Next one, computational procedure limitations. Again, like that model I mentioned, it's free, coming from Corps of Engineers. It says it's implicit, based on implicit method. There is no restriction on the time interval for stability. Well, that is true, but unfortunately, if you use too long time interval, then your results may not be accurate for sure, but sometimes may not be stable. Uncertainty in parameters. This is something over which you may or may not have much of control, but best you can do is that if you have uncertainty in any parameters, maybe friction factors, wave speed, etc., then what could you do? As engineers, we can't just say, well, since we don't know the data, we can't predict this. Well, in that case, you use your best estimate, but then do a sensitivity analysis, plus minus whatever is your uncertainty, 5%, 10%, and see what difference does it make. And then you make the decision on what is okay to do and what is not okay to do. So with this, I will close my presentation with this, how should I say, cartoon. You will be in charge of smartwatch project, but before I proceed further, it's going to refer to General Custer. Well, he is well known in American history, and this is related to his fight with the local Indians, and this is what happens. You will be in charge of our smartwatch project that is doomed from the start. Stop being such a pessimist, said General Custer to his horse. Question, why would he talk to his horse? Because even horse knew something was wrong. So in your case, if your horse is telling you or giving you impression something is wrong, that is the time to stop and look what needs to be done. So I stop here. Thank you very much.
That was a great presentation. I personally love Dilbert, so I think to end like a good way of placing the things in context. We have
Jose, but in the last presentation, there were some questions. If you think, since we have time, I will be happy to comment on those first before we take question answers. Could we? Or you want to leave those?
I think maybe you can get started with some comments on earlier questions.
Okay. All right. One question was on what do you do, or first of all was on if you are telling the client something and client is not what should you call very interested or raising some concern or questions or should we really do it or not, first item to do is show them like some of these pictures I have shown them, because they may not know water hammer, what is water hammer, what is transient flow, what it can do. Just show one or two pictures and say, if it is not done, this is what can happen and this is what will happen. If you are in the United States and a little bit, I would say in Canada, then next is if you don't do it, what our analysis is showing, something will happen like this, and lawyers will get involved, and that will be much, much more costly, not only dollar-wise, but reputation of the company and reputation of the government. Few cases I have been involved where there was water hammer, like in, I can't go more because of confidentiality reasons, because I have been involved in a number of cases. Northeast in the US, they were doing going to do some testing in the field on a water distribution system. Their records show that a particular well was closed, which it was not, and they tried to kind of reset some setting, and that generated a pressure. And as a result, the main one large butterfly well slammed shut, damaged or actually burst the pipeline. What was that? 78-inch line, which would be what, 6 feet, about 2.5 meters in diameter. There was no water in the city of over 300,000 to 400,000 people. Their hospitals had to delay surgeries because no water was there. State governor got involved, and the utility was under all kinds of pressure. And that is when I was contacted to come and see so that it doesn't happen, analyze it. And in that case, what did I find? Well, they had pressure relief valves. And since anytime there was a power trip, pressure relief valve will get activated, so there will be some water spilled out. So operators had closed those pressure relief valves. So my first suggestion to the lawyer was that it's just like you have a fire escape door in your building, but you have nailed it shut. So please get them operational. Second one on the case was, what happens if you are in between? Well, I had one experience, unfortunate, I should say, but which ultimately came out to be good, where there were two companies. Well, project was financed by IDB, project in Ecuador, and company from the United States was helping them to do the design. While difficulties arose, mainly I would personally feel it was a personnel problem. Communication between persons on either side were very kind of rigid, and that resulted in kind of serious miscommunications and difficulties. So I was called in to see who is right and who is wrong, which unfortunately I came to know after I landed in Quito. And while you look at what was raised and what was done, that was my job to evaluate and what should be done. But luckily in this case, it worked out very well because each side had some limitations, some drawbacks. So I could say, well, rather than saying who is right or wrong, let's see what needs to be done. So let's do it. And both sides were happy. And that's how it was resolved. Okay, I will now open to questions, answers.
No, those are very interesting points. And then my questions along those lines for you. But let's first look at the questions we have here on the Q&A.
Yeah.
I think the first three questions are actually linked to software.
Right.
So first one is a question on Transient. If
yes.
Is a code or a free software?
Say it again.
Transient. The
yes.
question, this is a code or a free software?
It's a code. It is not free.
It's a code. It's not free.
EPA net is free, but Trans EPA net is not.
And who is developing it?
We have developed it. Computer applications. Okay.
All right. Okay. Second question and third actually are about WH80. WH80, is it? Question is if it's free to download. Are there in the book applied transients examples of WH80? And I don't know if it's the same person who asked the question. There was a follow-up. If this is an evolution of WAMO.
Answer to the last one, no. This is based on method of characteristics. WAMO is based on implicit finite difference. Yep. Okay. Regarding the first one, no, it is not. I have sample small or rather short codes in the book, in the appendix. In first and second edition, they were included in the appendix, but it does not have like WH is rather long, comprehensive code. So it is not in the book, cannot be in the book. And yeah, it is not it's not downloadable. When we say cloud computing, we allow if somebody wants to use it, they can have arrangement with us. Yes.
All right. Okay. Well, continuing here, I think I'm going to try to rephrase the question here. Is linked to your talk and Mohammed's talk, and he basically the terms between model validation and model verification. Do you think there's any difference in the words or semantics or?
Well, English language, you know, is English language, so it's not my mother tongue. So I would say that verification and validation is more or less the same, but calibration is not.
Yes, exactly.
Calibration is where you change parameters to match what you want to have. So there is a difference between calibration and validation, or calibration and verification, but I don't think there is a difference between verification or validation, because verification is you are verifying, you are checking what results you are getting, they are okay. And validation is you have the result and you are checking, is your computer results okay. So yeah. Those both terms, personally, I feel are the same. Otherwise, go and read in the Webster dictionary. They might have a better explanation, but not from a person whose mother tongue is not English. I wouldn't go further. Maybe Brian Carney can add to it.
Well, I think that answers well, and I agree with you, because that tends to be lots of times in hydrology anyways, how people, hydrological modeling, how they call things calibration, validation, verification.
Right.
Now, the other question, I think that's the last one that we have here in the Q&A. And I'm going to read this. I would like to know if the reflection coefficients are system parameter and therefore constant regardless of the hydrodynamic conditions, or if they can also be treated as some sort of an unsteady phenomenon, such as unsteady friction.
Well, let me be careful how to answer that. It's a very good question. Question which, as I understand, is that you have reflection coefficient for a particular boundary, and you have one value during steady state when your wave comes. Does that reflection coefficient you have, is it time varying or does it remain constant? So answer would be, at least in my thinking, to start with, we don't know what even reasonable estimate is for a particular reflection coefficient. For example, for reservoirs, it will depend on how is the conduit connected to the reservoir. Is there a nice streamlined inlet, as is the case in all hydroelectric power plants, and most of the time in pumping plants as well? Or is it just some small tank and you have pipe coming in and you have just a sharp edge intake? So in each case, your reflection coefficient would be different. But the knowledge we have at this time, even coming up with one value is not known. So.
Oh, it's well.
And if you go to other boundaries, it becomes even more challenging.
Okay, I think that takes care of the Q&A question. I have just maybe one, and I don't think maybe there's enough time between me asking the question, and it could be something that's taken to the round table. But I find really one of the greatest challenges, at least here in, like you said, the United States, when it comes to litigation, is to educate the folks in a court level, when it gets to the court, to judges, to lawyers, to planners, to folks that are not engineers, to educate them about the risk. And we can show the videos, we can show the photographs, and hopefully we hope this actually shows it, right? But the other question I have is whether or not some of the sports would have their own technical staff. If they would have at least someone that has that's not linked to any litigation part. That someone that has any at a minimum some technical training to understand the language that's being used. And anyways, any thoughts on this?
I think that's an excellent comment. It's not just the judges and others. It is for engineering community itself to make it more kind of clear that what are the consequences if things are not done properly. Personally, as I mentioned, I have been working as consultant all over, and I think most of the countries still engineering is done at a pretty reasonable rigor. That is not the case in, well, still in Canada is better than US, but here, what is happening is companies get projects based on low cost.
Albeit, yeah.
And they do not have enough funds to do a proper study. And when it doesn't, and then they prepare some report very quickly to remain within the budget they have. And that is where difficulties arise. Sometimes it's okay, but other times, unfortunately, It causes lots of grief to all concerned, the client and as well as the general public. I think in Canada, I hope it is still the case, they used to have, whenever some consultant was being hired, they will ask two proposals which will be separate. One is the technical and another one would be the financial one. And they would not open the financial one till they had analyzed the technical part. So that kept that cost part out, which to my thinking for engineers, of course, money is always the major issue, but at the same time, we owe a large responsibility to general public as professional engineering professionals that work is done and done properly.
Yeah.
And that should start at undergraduate level. So that's where we have, I'm sure other universities do the same thing. We have ethics class, and then in other classes we try to bring in practicing engineers to discuss their projects, what they did, what they didn't do, where some are reasonably well in sharing where things didn't go well, and others, it is not the case. Well, look at the industries. For example, I showed you failures from what? Pumping systems and from hydropower. Have you seen anyone from oil pipeline or from a nuclear industry? Absolutely no. When I was writing the first edition, I tried and tried and tried. I would not even get response to my letter. Could you please share with me anything where you had some difficulty or something happens which shouldn't have happened? It is just not the case. I think in all these cases, I have been involved with one failure in Canada on oil line. And again, I can't even tell you the city. I can't tell you the client. Forget about the client, even what happened. All I can say is there was accident and it ended up in litigation.
Yeah,
It's a totally held and confidential, and that is where, unfortunately, human nature, you learn more when you see something as compared to when somebody tells you something. If you see something, what can happen, what has happened, it's much more effective as compared to just saying this might happen.
Yeah, this is a great point. And maybe again, this could be something that could be further discussed Friday. And
Yes.
well, I believe that we are at the top of the hour now, and this would conclude our first day here of the training course. On behalf of IAHR and all the panelists here, the organization, the speakers, really would like to thank everyone who has participated, the attendees for the questions, for the speakers to dedicate your time to share your knowledge with us. And tomorrow, this is going to be resumed as well. I don't know if there's any other information that we should share to the attendees at this point, or that's it.
We'll see you tomorrow at 12 Central Time, Central European Time.
European time.
Yeah, Central Time in US is different.
Chicago time. Perfect. All right, then. So thank you all for coming here and to participate. Again, thanks for all the speakers, and I will see you all tomorrow.
Thank you very much.
Bye.
Bye-bye. Thank you. Bye.
Thank you. Bye.